Hey there, night wanderers. Welcome back to another journey through the cosmos where we explore the universe's greatest mysteries while you settle in for the night. Picture this July 1st, 2025, midnight in Chile. While most of the world sleeps, astronomer Larry Deno sits alone in a dimly lit office, his eyes scanning an endless stream of data points flickering across his screen. Just another routine night of planetary defense work, checking for asteroids that might threaten Earth. He's done this thousands of times before. Click Analyze, Dismiss. Click Analyze, Dismiss. But then something appears that doesn't quite fit. A faint speck of light moving through the dense star fields near the galactic center. He pauses. His cursor hovers over the Dismiss button. In that single moment, humanity nearly missed the most significant cosmic discovery of the decade. What Larry was looking at wasn't just another near-Earth object. It was a visitor from another star system traveling for billions of years through the void of space, and we almost sent it straight to the digital trash bin. If you're as fascinated by the stories behind cosmic discoveries as I am, do me a favor and hit that like button. And if you want to drift off to sleep with the universe's most captivating mysteries every week, subscribe and turn on notifications. Trust me, your late night wandering mind will thank you. Now, let's talk about how close we came to missing one of the most extraordinary objects ever detected in our solar system. Because the story of 3I Atlas isn't just about what we found. It's about what we almost didn't see, and why that matters more than you might think. Larry Deno describes that moment with remarkable humility. I was the person reviewing at the time that 3I popped out of the pipeline, he told reporters later. And at the time, it looked like a completely garden variety new near-Earth object. Let's think about that for a second. The third confirmed interstellar visitor in human history, an object that had been traveling through our galaxy for potentially 14 billion years, looked completely ordinary to one of the world's experts in detecting cosmic threats. It's like finding the Hope Diamond in your backyard and thinking it's just a piece of broken glass. But here's where the story gets really interesting, and where we need to understand just how difficult celestial hide-and-seek actually is. The reason 3I Atlas was so hard to spot initially has everything to do with timing and location. During June 2025, as this interstellar wanderer approached our solar system, it was passing directly in front of the Milky Way's galactic center. Imagine trying to spot a single firefly in front of a massive stadium's floodlights. That's essentially what astronomers were up against. The galactic center is one of the most densely packed regions of stars visible from Earth. When you point a telescope there, you're looking at millions upon millions of stars all crowded together in the night sky. Every single point of light could potentially be a moving object, or it could just be a distant sun sitting still in space. The Atlas system, brilliant as it is, takes images of the same patch of sky at different times and looks for things that move. But when you're dealing with this cosmic traffic jam of starlight distinguishing genuine movement from noise, becomes extraordinarily challenging. It's like trying to track a specific car in satellite images of Los Angeles rush hour traffic, except the cars don't stay in lanes and some of them are billions of miles away. This brings us to something called pre-discovery observations, and it's one of the most fascinating aspects of modern astronomy. See, once Larry flagged this object as potentially interesting, astronomers around the world went back through their archives. They started looking at images they had already taken weeks or even months earlier, searching for this same object. And they found it. The Zwicky Transient Facility at Palomar Observatory in California had captured 3I Atlas on June 14th, 2025, more than 2 weeks before the official discovery. Atlas's own telescopes in Hawaii and South Africa had recorded it multiple times between June 5th and June 29th. The data was already there sitting in computer servers, but nobody had recognized what they were looking at. This happens more often than you'd think in astronomy, and it's not because astronomers are careless. Amateur astronomer Sam Dean, who has made a career out of finding these pre-discovery images, noted that 3I Atlas was simply too faint and too embedded in those dense star fields to trigger automatic detection systems. The software that scans these images is looking for specific signatures, particular brightnesses, certain rates of movement objects that stand out clearly from the background. 3I Wace Atlas was playing hard to get moving through the cosmic equivalent of camouflage. Let's put this in perspective with some history, because the story of missed discoveries is as old as astronomy itself. In 1781, William Herschel discovered Uranus, the first planet found with a telescope. But here's the thing. At least 22 astronomers had observed Uranus before Herschel, dating all the way back to 1690. John Flamsteed, the first astronomer, Royal of England, saw it in 1690 and catalogued it as a star called 34 Tauri. He saw it. He recorded it. He just didn't recognize what it was. Nearly a century passed before someone looked at that same point in the sky and realized it was moving, that it was orbiting the sun, that it was a planet. Or consider Pluto, discovered officially in 1930 by Clyde Tombaugh. Right, except Pluto appears on photographic plates taken at the Yerkes Observatory in 1909, more than 20 years earlier. It's right there in the images, but nobody noticed. Even more remarkably, in 1915, Pluto was photographed twice in a span of weeks. And had anyone compared those two images carefully, they would have seen it had moved. They would have discovered Pluto 15 years early, but they didn't. The images sat in archives while Pluto continued its slow orbit unrecognized. The lesson here isn't about failure. It's about the sheer difficulty of finding needles in cosmic haystacks. Every single night, telescopes around the world capture millions of data points. They photograph billions of stars, galaxies, asteroids, and cosmic phenomena. The amount of data is overwhelming. The human eye and mind, no matter how trained, can't possibly review it all. That's where systems like Atlas come in. Atlas the asteroid, terrestrial impact. Last Alert System is actually a network of 4 telescopes spread across the globe, 2 in Hawaii, 1 in Chile, and 1 in South Africa. These aren't massive observatory telescopes. They're relatively small, with mirrors just half a meter wide, but what makes them special is their wide field of view. Each Atlas telescope can survey huge swaths of the sky every night, automatically taking images and comparing them to previous nights. The system was designed with a specific mission to find asteroids that might hit Earth and find them with enough warning time to actually do something about it. Think about that mission for a moment. These telescopes are essentially standing guard over our planet, watching for rocks that could cause catastrophic damage if they struck Earth. They need to scan the entire visible sky. Every couple of nights, identify anything moving, calculate trajectories, and flag potential threats. It's an enormously complex task, and it works remarkably well. Atlas has discovered hundreds of near-Earth asteroids since it came online. It's found comets. It's even detected supernovae in distant galaxies. And now, almost by accident, it's found something even more extraordinary, a visitor from interstellar space. But here's what makes Larry Deno's discovery moment so crucial to understanding modern astronomy. When that faint point of light appeared on his screen, it triggered what's called the human-in-the-loop system. Despite all our advanced computers and AI algorithms, we still need human eyes and human judgment at critical moments. The Atlas software had flagged this object as unusual, but it was Larry who had to make the call. Is this worth investigating further, or is it just a glitch, a distant star, or one of the countless pieces of space debris that orbit our sun? He chose to investigate. He sent out alerts to other observatories. Within hours, telescopes around the world were swinging toward this tiny, faint object. The Deep Random Survey Telescope in Chile got a look. The Lowell Discovery Telescope in Arizona pointed its mirror skyward. The Canada-France-Hawaii Telescope atop Mauna Kea, one of the premier observatories in the world, dedicated precious observation time to this mysterious speck, and what they saw made them realize Larry had found something remarkable. On July the 2nd, just one day after the initial detection, multiple observatories reported the same thing: this object had a coma. For those of you just getting into astronomy, a coma is that fuzzy cloud of gas and dust that surrounds a comet's nucleus. It forms when ice on the comet's surface heats up and turns directly from solid to gas, a process called sublimation, releasing dust particles that had been frozen in the ice. The presence of a coma was significant for two reasons. First, it confirmed this was a comet, not an asteroid. Second, and more importantly, comets from our solar system don't develop strong comas when they're still this far from the sun. This thing was behaving differently. It was releasing gas and dust in ways that suggested it might not be from around here. Astronomers David Jewett and Jane Liu, both legendary figures in planetary science who have discovered dozens of objects in our outer solar system, turned the Nordic Optical Telescope toward 3I Atlas that same day. Their images showed what they described as clearly active behavior. The comet wasn't just passing through quietly. It was responding to the sun's heat, waking up from billions of years of frozen sleep, putting on a show. By this point, the astronomical community was buzzing. The Minor Planet Center, the international organization that officially catalogs new discoveries in our solar system, had collected observations from 31 different observatories. They'd compiled 122 separate data points about this object's position and movement. And when they ran the numbers calculating the trajectory backwards and forwards in time, they discovered something that sent chills down the spines of everyone involved. This object's orbital eccentricity was off the charts. We'll dive deep into what that means in our next section, but for now, notice the math showed definitively that this object didn't come from our solar system. It came from somewhere else. It came from the stars. The Minor Planet Center made it official on July 2nd, 2025. They gave it the designation 3I, meaning the third confirmed interstellar object. They also gave it the comet designation C2025N1, following the standard naming convention. But everyone from professional astronomers to space enthusiasts around the world simply called it 3I Atlas, honoring the system that found it. Now here's a question worth pondering as you drift towards sleep tonight. How many of these interstellar visitors have we missed? Think about it. We've only confirmed 3 interstellar objects in all of human history. Oumuamua in 2017, Borisov in 2019, and now Atlas in 2025. But statistical models suggest that at any given time, there should be several interstellar objects passing through the inner solar system. Some estimates put the number at 1 or 2 per year. So, where are they? The answer is probably exactly where 3I Atlas almost ended up in the noise, lost in the dense star fields, too faint to trigger our detection systems. Moving at angles we don't usually monitor, passing through during bad weather at major observatories, or simply overlooked by tired astronomers reviewing their 10,000th data point of the night. The universe is vast beyond human comprehension, and these cosmic wanderers are small and dark and fast. Finding them requires not just advanced technology, but also perfect timing, and frankly, a bit of luck. This is why Larry Deno's decision to investigate that faint point of light matters so much. It reminds us that for all our technological sophistication, for all our automated systems and artificial intelligence and massive databases, science still depends on human curiosity. It depends on someone looking at something ordinary and thinking, wait, let me check that again. It depends on someone trusting their instincts when the computer says everything is routine. It depends on someone being willing to sound the alarm, even when they're not entirely sure. And sometimes that curiosity leads us to discover we're not alone in the cosmic ocean. That other star systems create comets too. That the galaxy is full of wanderers drifting between the stars. That on a random Tuesday night in July, something from unfathomably far away comes close enough that we can see it, study it, and learn from it. But 3I Atlas isn't just any interstellar visitor. As we're about to explore, it's part of a very exclusive family, a cosmic trio that's teaching us things about the universe we never imagined we could learn. Each of these three objects tells a different story, reveals different mysteries and challenges our understanding in unique ways. So, let's meet the family, shall we? Let's talk about what makes each of these interstellar wanderers special, and why 3I Atlas might just be the most extraordinary one yet. Three visitors from beyond, three completely different personalities, and each one has rewritten what we thought we knew about the space between stars. In October 2017, a telescope in Hawaii detected something moving through our solar system at impossible speeds, following a trajectory that defied every rule we knew. Scientists named it Oumuamua Hawaiian for scout, or messenger from afar arriving first. But here's the twist. We still don't know what it actually was. No coma, no tail, an elongated shape like nothing we'd ever seen, and an acceleration that made physicists scratch their heads in confusion. Some scientists suggested it was propelled by reflected sunlight. Others whispered about possibilities they barely dared to publish. 2 years later, in 2019, amateur astronomer Gennady Borisov spotted our second confirmed interstellar visitor, a well-behaved comet that looked exactly like we expected comets to look. And now in 2025, 3I Atlas arrives, breaking every record the first two set, and raising entirely new questions about what's really out there in the dark between stars. If you're captivated by these cosmic mysteries, as much as I am, show some love with a like. And subscribe so you never miss a journey through the universe's most mind-bending discoveries. Your future self drifting off to sleep with the cosmos will appreciate it. Let's start with Oumuamua, because this is where everything changed. Before October 19th, 2017, interstellar objects were purely theoretical. We knew they had to exist. The math demanded it. When stars form, they create massive disks of gas and dust that eventually collapse into planets, asteroids, and comets. Not everything gets captured by gravity. Some objects get flung out into interstellar space through gravitational interactions, especially with giant planets like Jupiter. Our own solar system has probably ejected billions of comets into the void over its 4.6 billion year history. So logically, other star systems must do the same thing. The galaxy should be filled with homeless cosmic wanderers. But we'd never actually seen one. Not until astronomer Robert Warwick, working with the Pan-STARRS telescope on Haleakala in Hawaii, noticed something strange in his data. What made Oumuamua immediately suspicious was its speed. It wasn't just moving fast, it was moving too fast to be orbiting the sun. When astronomers calculated its trajectory, they found an orbital eccentricity of 1.2. Now, for those keeping score at home, any eccentricity above 1.0 means an object is on what's called a hyperbolic trajectory. It's not in a closed orbit, it's just passing through, never to return. Our fastest space probes, Voyager 1 and 2, have eccentricities around 3.0 relative to the Sun, because we deliberately launch them on escape trajectories. But natural objects in our solar system, their eccentricities are all below 1.0. Even the most elongated comet orbits top out around 0.995. An eccentricity of 1.2 screamed outsider, but the weirdness was just beginning. As telescopes around the world tracked Oumuamua during its brief visit, they noticed something that still causes heated debates in astronomy conferences today. The object was tumbling end over end, completing a rotation about every 7.3 hours. And as it tumbled, its brightness varied dramatically by a factor of 10. The only way to explain such extreme brightness changes is if the object is highly elongated. The best models suggest Oumuamua is somewhere between 100 to 1,000 meters long, but only about 1/10 that wide. Imagine a cosmic cigar, or as some researchers suggested, more like a pancake spinning through space. We've never seen anything quite like it. Then came the acceleration anomaly. And this is where things get really interesting. In June 2018, long after Oumuamua had left the inner solar system and was racing back toward interstellar space, astronomers noticed something peculiar in their trajectory data. The object wasn't following a simple gravitational path. It was accelerating, slightly deviating from where pure Newtonian physics said it should be. The excess acceleration was tiny, just 0.005 meters per second squared, but it was definitely there, and it was consistent. For normal comets, this kind of acceleration is easy to explain. As they approach the sun, ice on their surface heats up and sublimates, turning directly from solid to gas. This gas jets off into space, and through Newton's third law, every action has an equal and opposite reaction. The escaping gas pushes the comet slightly. We see this all the time. It's called the rocket effect, or outgassing. But here's the problem. Oumuamua showed no signs whatsoever of cometary activity. No coma, no tail, no dust, no gas emissions that any telescope could detect. So, what was pushing it? The scientific explanations range from the mundane to the exotic. Maybe it was outgassing just very weakly with particles we couldn't detect. Maybe it was made of hydrogen ice, which would sublime without leaving visible traces. Maybe solar radiation pressure was pushing it photons from the sun, physically bouncing off its surface and transferring momentum. Or maybe, and this is where Harvard astronomer Avi Loeb enters our story, maybe it was something else entirely. Loeb proposed in a peer-reviewed scientific paper that made headlines worldwide that Oumuamua could be a light sail, an artificial structure built by an alien civilization pushed through space by starlight. The elongated shape, the unusual acceleration, the lack of outgassing it all fit. Now, most astronomers strongly disagreed with this hypothesis. They argued that natural explanations, while requiring some special conditions, were far more likely than jumping to alien technology. But Loeb's willingness to seriously consider the possibility sparked a crucial conversation about how we search for extraterrestrial intelligence and what we do when we encounter something truly anomalous. Here's what we can say with certainty about Oumuamua. It came from the direction of the star Vega, taking about 300,000 years to travel from there to us. It passed closest to the Sun on September 9, 2017, coming within 0.25 astronomical units closer than Mercury's orbit. It reached a peak speed of 87.7 kilometers per second relative to the Sun. By the time we discovered it, it was already leaving. Astronomers had only a few weeks to gather data before it became too faint to observe. And now, it's gone heading toward the constellation Pegasus, and we'll never see it again. 2 years of debate, speculation, and analysis followed. Scientists wrote papers arguing for natural explanations. Others wrote papers challenging those explanations. The astronomical community learned a hard lesson. When you only have a few weeks of data on a completely unprecedented object, you're left with more questions than answers. We needed another interstellar visitor, one we could study more thoroughly. And in August 2019, we got our wish. Gennady Borisov wasn't using a massive professional telescope when he made his discovery. He was using a telescope. He built himself a 0.65 meter reflector at the Margot Observatory in Crimea. On August 30th, 2019, he noticed a new fuzzy object in his images. He reported it to the Minor Planet Center. And within days, astronomers realized they were looking at something special. This object, designated 2I Borisov, had an orbital eccentricity of 3.4, substantially higher than Oumuamua's 1.2. This thing was moving even faster, and it was unquestionably interstellar. But unlike Oumuamua, Borisov looked exactly like a comet should look. It had a bright coma. It developed multiple tails as it approached the sun. Spectroscopic analysis detected the chemical signatures of sublimating ice water, carbon monoxide cyanogen. This was clearly a dirty snowball from another star system, and it behaved just like comets from our own solar system. In many ways, 2I Borisov was reassuringly normal, and that normalcy was scientifically valuable. The comet's composition told us something profound. Comet formation processes around other stars produce similar results to our own solar system. The ratio of carbon monoxide to water in Borisov's coma was higher than in most solar system comets, suggesting it formed in a colder region around its parent star. But the fundamental chemistry was familiar. We even detected sodium and potassium in its spectrum elements we see in solar system comets. The universe, it turns out, uses similar recipes, even when it's cooking in different kitchens. Borisov's trajectory analysis revealed it came from the direction of the constellation Cassiopeia, from a region of space associated with the local interstellar cloud. It traveled for millions, possibly billions of years before stumbling into our solar system. At its closest approach to the Sun in December 2019, it passed within 2 astronomical units, roughly twice Earth's distance from the Sun. Astronomers tracked it for months, gathering spectra, measuring its rotation, analyzing its outgassing patterns. Unlike Oumuamua's brief flyby, Borisov gave us time to really study an interstellar object properly. And then it did something spectacular and tragic. In March 2020, as Borisov was heading back to interstellar space, the Hubble Space Telescope captured images showing the comet's nucleus had fragmented. A chunk roughly half the size of the main nucleus broke off, creating a second bright spot in the coma. This kind of fragmentation isn't unusual for comets. The thermal stress of approaching the Sun, combined with the explosive release of gas from sublimating ice, can crack nuclei apart. But watching an interstellar visitor literally break apart added a poignant note to its departure. This comet had survived perhaps billions of years in the cold between stars, only to shatter during its brief encounter with our Sun. Now, we come to 3I Atlas, and this is where the records start falling like dominoes. Remember those eccentricity numbers: Oumuamua at 1.2, Borisov at 3.43I, Atlas comes screaming in at 6.139. That's not just higher, that's categorically different. To understand what this means, we need to think about what eccentricity actually represents. It's a measure of how much an orbit deviates from a perfect circle. A circle has an eccentricity of 0. Earth's orbit is nearly circular, with an eccentricity of 0.017. Halley's Comet, with its extremely elongated elliptical orbit, has an eccentricity of 0.967. When you hit 1 point, you've reached parabolic velocity, the minimum speed needed to escape the Sun's gravity. Anything above 1.0 means you're going faster than escape velocity. You're on a one-way ticket out, but 6.139. That's a hyperbolic trajectory so extreme that the path looks almost like a straight line through the solar system. 3I Atlas isn't just passing through. It's blazing through at such ridiculous speed that the Sun's enormous gravity barely bends its trajectory. Think of it this way. Imagine throwing a tennis ball through a wind tunnel. A gentle toss might curve significantly as the air deflects it. But fire that ball from a cannon at supersonic speed and it punches through in an almost straight line. That's 3I Atlas. This extreme eccentricity translates to extreme speed. At perihelion, its closest approach to the Sun on October 29, 2025, 3I Atlas was moving at 68 kilometers per second with respect to the Sun. That's 152,000 miles per hour. By comparison, Earth orbits at a leisurely 30 kilometers per second. The New Horizons probe, which became the fastest object humanity ever launched, left Earth at about 16.5 kilometers per second. 3I Zor Atlas is moving more than 4 times faster than our speediest spacecraft, and it achieved that speed naturally through its journey across the galaxy. Here's something that should make you pause and wonder, where does that speed come from? Objects in our solar system are gravitationally bound to the sun. They orbit, they return. Their speeds are determined by their distance from the sun and conservation of energy. But interstellar objects bring velocity with them from outside the solar system. That velocity represents their motion through the galaxy, their orbital path around the Milky Way's center, and any gravitational kicks they receive from stars they passed along the way. 3I Atlas's incredible speed tells us it's been on a very different journey than Oumuamua or Borisov. Let's talk about trajectory inclination, because this reveals something fascinating about cosmic randomness. Oumuamua came in at an angle of about 122 degrees to the ecliptic, the plane in which Earth and the other planets orbit. It approached from above the solar system's plane, swooped down through, and exited below. Borisov came in at about 44 degrees, entering from a much shallower angle. But 3I Atlas, its trajectory is inclined at 175 degrees, which means it's moving in almost exactly the opposite direction of the planet's orbits. It's retrograde, traveling backward compared to the solar system's rotation. Imagine all the planets as cars on a circular highway, all driving counterclockwise. Oumuamua came from a side street at an angle. Borisov merged from an on-ramp. But 3I Atlas is the cosmic equivalent of entering the highway going the wrong way at maximum speed. This retrograde motion is incredibly rare for natural solar system objects. It suggests this comet has been traveling through the galaxy on a very different path than our sun, possibly for an immensely long time. Now, let's address the elephant in the room, or rather the three elephants each from a different part of the galaxy. What are the chances that we detect 3 interstellar objects in just 8 years, after never detecting any in all of human history before 2017? Does this mean they're common, or did we just get incredibly lucky? The truth is somewhere in between. Statistical models based on our 3 detections suggest that on average about 1 interstellar object larger than 200 meters in diameter passes within Earth's orbit every year. Smaller objects are even more common. The galaxy is absolutely teeming with these cosmic wanderers ejected from their birth systems and drifting through space for eons. But here's the catch: they're incredibly hard to detect. They're small, dark, moving fast, and they spend most of their time in the vast emptiness between stars where no one is looking. We only started detecting them recently because our telescopes got better. Pan-STARRS, which found Oumuamua, came online in 2010. The Atlas system achieved full operational capability around 2018. These wide-field survey telescopes scan huge areas of sky every night, specifically looking for moving objects. Before these systems existed, an interstellar object could zip through the inner solar system, and we'd never know. It happened countless times throughout human history. Ancient astronomers saw comets and meteors, but they had no way to calculate trajectories or determine origins. How many interstellar visitors passed through during the Renaissance, during the Roman Empire, during the age of the dinosaurs, completely unnoticed? Here's something to consider as your mind drifts. Each of these 3 objects represents a sample size of one from potentially billions of interstellar wanderers. Oumuamua might be unusual even among interstellar objects, or it might be perfectly normal, and our solar system comets are the weird ones. Borisov might represent the typical interstellar comet, or it might be an outlier. 3I Atlas, with its extreme speed and ancient origins, might be a rare cosmic elder, or the galaxy might be full of similar speedsters, and we just happen to catch this one. What I find most beautiful about this interstellar family isn't their differences, though. Those are scientifically invaluable. It's what they represent collectively. For all of human history, we've looked up at the stars and wondered what else is out there. These 3 objects are physical pieces of out there delivered directly to us. They're not just data points or distant specks of light. They're actual matter from other star systems material that formed around different suns, that experienced different histories, that traveled incomprehensible distances to briefly pass through our neighborhood. and each one teaches us humility. Oumuamua taught us that the universe can present us with things we don't understand, and that's okay. We don't have to have all the answers immediately. Borisov taught us that, despite the universe's vastness and variety, some fundamental processes produce similar results everywhere, connecting us to the cosmos in ways we're only beginning to understand. And 3I, Atlas. Well, as we're about to discover, this cosmic speedster is teaching us about time itself, about the deep history of our galaxy, about what happens to objects that wander through space for billions of years. But to understand those lessons, we need to talk about the mathematics of extreme motion, about what it means to travel through space on a trajectory so hyperbolic it defies easy comprehension. So, let's dive into the numbers, shall we? Let's explore exactly what happens when an object moves so fast that even the sun's gravity can barely touch it. Imagine standing on a beach watching a bullet train pass by at full speed. Now, imagine that train is moving so fast that even gravity itself can barely make it turn. That's what we're dealing with when we talk about 3I Atlas. Most people think gravity is this all-powerful cosmic force that controls everything in space, pulling planets into neat circular orbits and keeping comets tethered to the sun. But here's the truth that physicists have known for centuries but rarely talk about: gravity isn't all-powerful. It's actually quite weak. And when something is moving fast enough, gravity becomes more of a gentle suggestion than a command. 3I Atlas is moving so absurdly fast that the sun, with all its enormous mass, all its gravitational might, can barely deflect its path. The math behind this is both beautiful and terrifying, and it reveals something profound about the nature of motion itself, about escape, about freedom, and about what happens when an object has been wandering the galaxy for so long that nothing, not even a star, can hold it back. If you're the kind of person who finds beauty in equations that describe cosmic freedom, hit that like button. And subscribe, because we're going deep into the mathematics of the universe. And trust me, it gets more mind-bending from here. Let's start with the number 6.139. That's the orbital eccentricity of 3I Atlas. And to most people, it's just an abstract decimal. But to anyone who understands orbital mechanics, this number is shocking. It's the kind of number that makes astronomers do double takes and recalculate their data because it seems too extreme to be real. To understand why we need to talk about what eccentricity actually measures and why it matters so much. Eccentricity is fundamentally about shape. An orbit with zero eccentricity is a perfect circle. The object maintains constant distance from what it's orbiting. Increase the eccentricity to 0.5, and you get an ellipse and oval shape where the object gets closer and farther from the central body in a predictable pattern. Push it to 0.9, and that ellipse becomes very elongated, cigar-shaped. The object spends most of its time far away, then whips around the central body at high speed before heading back out. But something magical happens at eccentricity 1.0. This is the boundary between two completely different types of motion. Below 1.0, you have closed orbits. The object is bound. It will return. It's a prisoner of gravity, forever cycling through the same path. At exactly 1.0, you have a parabolic trajectory. The object has precisely escape velocity, the minimum speed needed to break free. It's balanced on the edge of freedom, moving just fast enough that it will never come back, but not fast enough to have any velocity left over once it escapes. Above 1.0, and this is where 3I Atlas lives, you have hyperbolic trajectories. These are open curves, unbounded paths. The object isn't just escaping, it's escaping with energy to spare. At eccentricity 1.1, you're going slightly faster than escape velocity. At 2.0, you're moving substantially faster. At 3.4, Borisov's eccentricity, you're racing away with significant excess velocity. But at 6.139, you're moving so fast relative to the sun's escape velocity that the solar system is just a brief interruption in your otherwise nearly straight-line path through the galaxy. Here's a way to visualize this. Imagine the sun's gravity as a rubber sheet stretched tight with the sun, creating a deep depression in the center. A planet like Earth rolls around this depression in a circular or elliptical path, never having enough speed to climb out. A comet from the Oort cloud might swing through on a highly elliptical orbit, climbing far up the sheet before sliding back down. An object with parabolic trajectory would have just enough energy to climb out and reach the flat region beyond, but it would arrive there with zero velocity, completely exhausted. But 3I's Atlas. It's more like a meteor slamming into the sheet at supersonic speed. It barely even notices the depression. The sun's gravity warps its path slightly, creating a gentle curve, but the object has so much kinetic energy that it punches through and out the other side, still moving at tremendous speed. The mathematical term for this is a hyperbola, one of the conic sections that the ancient Greeks studied thousands of years ago, never imagining that these elegant mathematical curves would one day describe the paths of cosmic wanderers from other star systems. Now let's translate this into actual velocities, because numbers make this visceral. At perihelion, when 3I Atlas passed closest to the Sun at a distance of 1.36 astronomical units, about 203 million kilometers, it was moving at 68 kilometers per second. To put that in perspective, a bullet from a high-powered rifle travels at about 1 kilometer per second. 3I Atlas is moving 68 times faster than a speeding bullet. In 1 second, it covers 68 kilometers, roughly the distance from Washington, D.C. to Baltimore. In 1 minute, it travels 4,080 kilometers farther than the width of the continental United States. But here's what really matters. That's not its total velocity. That's just its velocity relative to the sun at its closest approach. When 3I Atlas is far from the sun, where gravity's influence fades to nearly nothing, it still retains what's called hyperbolic excess velocity. This is the leftover speed it has after accounting for everything the sun's gravity did to it. For 3I Atlas, this excess velocity is enormous, which is exactly what produces that extreme eccentricity of 6.139. Compare this to humanity's fastest spacecraft. When New Horizons launched toward Pluto in 2006, it left Earth at 16.26 kilometers per second, relative to the Sun, making it the fastest object we've ever sent into space. That was fast enough to reach the Moon in just 9 hours, to pass Jupiter's orbit in just over a year. But 3I Atlas is moving more than 4 times faster than that. If you could somehow board 3I Atlas and ride it like a cosmic surfboard, you could travel from Earth to the Moon in about 90 minutes. You'd reach Mars's orbit in about a week. You'd cross the entire solar system from the Sun to Neptune's orbit in just a few months. The Voyager probes launched in 1977 are now the farthest human-made objects from Earth, traveling at about 17 kilometers per second relative to the Sun. They have been flying for nearly 48 years and have barely scratched the edge of what we call the solar system's sphere of influence. At their current speed, they'll take about 40,000 years to reach the distance of the nearest star. But 3I Atlas, moving 4 times faster, would cover the same distance in about 10,000 years. Still an incomprehensibly long time by human standards, but in cosmic terms, it's traveling at what we might call express speed through the galaxy. Now, here's a question that might be nagging at your mind. If this thing is moving so fast, why doesn't its trajectory look like a straight line when we plot it? Why can we see a curve at all? This is where the scale of the solar system becomes important. Even though 3I Atlas has an extremely hyperbolic trajectory, and even though it's moving absurdly fast, the sun's gravity is still doing something. It's just doing it very subtly. Think of it this way. If you zoomed out far enough to see 3I Atlas's entire path through the galaxy spanning light years, its passage through our solar system would look like a barely perceptible wiggle, a tiny deflection in an otherwise straight line. But when we zoom into the scale of the inner solar system, a region just a few astronomical units across that tiny deflection becomes measurable. We can see the curve. We can calculate how much the sun's gravity bent the trajectory. And from that calculation, we can work backwards to figure out where the object came from and where it's going. This is exactly what astronomers did. They tracked 3I Atlas as it approached the sun past perihelion and began its exit from the inner solar system. They measured its position night after night, accumulating data points. They plugged these measurements into equations first derived by Johannes Kepler in the 1600s and refined by Isaac Newton and countless others since then. And they found something remarkable when you trace the trajectory backwards in time before the sun's gravity affected it. 3I. Atlas was moving through the galaxy from the direction of Sagittarius near the galactic center. But there's more. Astronomers don't just calculate trajectory direction. They break down the object's velocity into three components using the galactic coordinate system. There's the U component, which measures radial velocity motion toward or away from the galactic center. There's the V component measuring transverse velocity motion in the direction of galactic rotation. And there's the W component measuring vertical velocity motion perpendicular to the galactic plane. For 3I Atlas, the U component is -51 kilometers per second. That negative sign means it's moving away from the galactic center. It's heading outward through the Milky Way. The W component is positive 18.5 kilometers per second, meaning it's moving upward through the galactic disk. These numbers tell us something profound. 3I Atlas doesn't orbit in the flat plane of the galaxy like our sun does. It's on a tilted orbit plunging up and down through the galactic disk as it circles the Milky Way's center. That vertical velocity of 18.5 kilometers per second is unusually high. Most stars in our neighborhood have much smaller W velocities, typically just a few kilometers per second. They orbit roughly in the galactic plane, like cars on a flat highway. But 3I Atlas is more like a plane that periodically climbs and dives through the highway level. This kind of motion is characteristic of what astronomers call thick disk, or halo populations, older stellar objects that formed when the galaxy was younger and more chaotic, before settling into its current flattened disk structure. Now, let's talk about a common misconception, because this trips up even scientifically literate people. When you hear that something has escape velocity, it's tempting to think there's a specific speed you need to reach, like breaking the sound barrier. Hit that magic number, and suddenly you're free of gravity. But that's not quite right. Escape velocity isn't a fixed number. It depends on where you are. Earth's escape velocity at the surface is about 11.2 kilometers per second. But if you're already at the altitude of the International Space Station, you need less speed to escape because you're farther from Earth's center and gravity is weaker. If you're at the moon's distance, you need even less. Escape velocity decreases with distance according to a square root relationship. Double your distance from Earth's center, and escape velocity drops by a factor of the square root of 2, about 1.414. The same principle applies to escaping the sun. At Earth's distance, solar escape velocity is about 42 kilometers per second. At Jupiter's distance, it's only about 18 kilometers per second. Out at Neptune's orbit, it drops to about 7.5 kilometers per second. And this is where 3I Atlas's extreme speed becomes even more impressive. When it passed perihelion at 1.36 AU, solar escape velocity at that distance is roughly 35 kilometers per second. But 3I Atlas was moving at 68 kilometers per second, nearly twice escape velocity at that point. It has so much excess energy that even at its closest approach to the sun, it was never in danger of being captured. Here's another way to think about this that might help it click. In physics, we often talk about energy rather than velocity because energy is more fundamental. Kinetic energy. The energy of motion scales with the square of velocity. Double your speed, and you quadruple your kinetic energy. Escape from a gravitational well requires a certain amount of energy to overcome gravitational potential energy. An object with exactly escape velocity has just enough kinetic energy to cancel out the gravitational potential energy at infinity. An object with hyperbolic trajectory has excess kinetic energy left over. For 3I Atlas, with its eccentricity of 6.139, the math works out such that its kinetic energy is vastly greater than what's needed to escape. Specifically, the ratio of kinetic energy to the energy needed for escape is related to eccentricity. Without getting too deep into the equations, that eccentricity of 6.139 means 3I Atlas has roughly 38 times more kinetic energy than the minimum needed to escape the sun's gravity. It's not just free, it's extravagantly free. It's the cosmic equivalent of someone who quit their job and has enough money to travel the world for decades without worry. This brings us to a beautiful and slightly melancholy aspect of hyperbolic trajectories. They're one-time events. 3I Atlas will never return to our solar system, ever. Its path is open, unbounded. In 1,000,000 years, in 1,000,000,000 years, it will still be out there moving through the galaxy, getting progressively farther from our sun. The only way it could return is if something dramatically changed its velocity, like a close encounter with another star. But space is so vast and stars are so far apart that such encounters are extraordinarily rare. Think about what this means. 3I Atlas has been traveling through space for billions of years, as we'll explore more deeply in the next section. It's passed by countless stars through vast molecular clouds across spiral arms of the galaxy. And now it's passed by our star, our sun, the only star humanity has ever known, up close. For a brief moment measured in months, this ancient wanderer intersected with our tiny corner of the cosmos. We saw it, we studied it, we learned from it, and now it's leaving, continuing its eternal journey through the Milky Way, and we'll never see it again. There's something both beautiful and tragic about that, don't you think? This cosmic encounter, this intersection of paths, happens once and only once. It's like two strangers passing on a street, making eye contact for just a moment, before walking on, each continuing their separate journey, never to meet again. Except, in this case, one stranger is a 4.6 billion-year-old solar system with life and consciousness and curiosity, and the other is a frozen ball of ice and rock that's been wandering the galaxy since before Earth even existed. The mathematics of hyperbolic trajectories gives us the ability to calculate exactly where 3I Atlas came from and where it's going. It's deterministic. The equations don't lie, but they can't tell us the whole story. They can't tell us what this comet has seen in its billions of years of wandering. They can't describe the stars, its paths, the nebulae, its traversed the cosmic events it's witnessed. For that, we need to think about time itself, about the deep history of our galaxy, about what it means to be an object that's older than our solar system, that's been traveling through space since the universe was young. And that's exactly where we're headed, because 3I Atlas isn't just fast, it's ancient. And its age tells us a story about the galaxy itself, about stellar populations and galactic evolution, and the long, slow dance of matter through space and time. So, let's travel way back to an era when the Milky Way looked very different than it does now, when 3I Atlas was young. Close your eyes for a moment and try to imagine 14 billion years. You can't, can you? Neither can I. The human brain simply isn't wired to comprehend that kind of time span. The entire history of human civilization from the first cities to the space age spans maybe 10,000 years. Modern humans have existed for roughly 300,000 years. The dinosaurs ruled Earth for 165 million years. Our planet itself is 4.6 billion years old, but 14 billion years. That's almost as old as the universe itself, which began 13.8 billion years ago, with the Big Bang. And yet, according to the best statistical analysis we have, there's a strong possibility that 3I Atlas has been wandering through space for somewhere between 7.6 and 14 billion years. Think about that. This frozen ball of ice and rock might have formed when the universe was barely 1 billion years old, when the very first galaxies were still coalescing from primordial gas, when the Milky Way itself was just beginning to take shape. This isn't just a comet, it's a time traveler, a messenger from an epoch so ancient that it makes our entire solar system look like a newborn by comparison. If the idea of touching something older than Earth itself fascinates you, show some appreciation with a like. And subscribe to keep exploring these cosmic time capsules with me, because the universe's history is written in objects like this, if we know how to read them. Let's start with the science behind that age estimate, because it's not like there's a cosmic birth certificate attached to 3I Atlas. The researchers led by Matthew Hopkins at the University of Oxford used a brilliant statistical approach. They analyzed the orbital characteristics of 3I Atlas, specifically those velocity components we talked about earlier, the UV and W velocities that describe how it moves through the galaxy. Then they compared these characteristics to what we know about different stellar populations in the Milky Way. Here's the key. Insight stars aren't all the same. Age and different generations of stars have different orbital properties. The galaxy has been making stars for billions of years, and we can divide these stars into populations based on when they formed. The youngest stars, called Population 1, orbit mostly in the flat galactic disk, have nearly circular orbits, and are relatively rich in heavy elements. Our Sun is a population Wang, star born about 4.6 billion years ago, from a cloud of gas that had already been enriched by previous generations of supernovae. Then there are older stars, population 2, which formed much earlier in the galaxy's history. These stars have more eccentric tilted orbits. They're found in the galactic halo and in what's called the thick disk, a puffed-up region surrounding the main disk. And crucially, they have lower metallicity astronomer speak for fewer heavy elements because they formed from more primordial material before as many supernovae had occurred to create heavy elements. Now, comets don't emit light like stars, so we can't directly measure their composition the same way. But they do move, and their motion tells a story. 3I Atlas's vertical velocity of 18.5 kilometers per second is unusually high. Most young stars and objects in our solar neighborhood have vertical velocities of just a few kilometers per second. They stick close to the galactic plane like cars on a highway. But 3I Atlas is bouncing up and down through the galaxy with significant energy. Hopkins and his team ran simulations creating millions of model orbits for objects of different ages and comparing them to the observed properties of 3I Atlas. What they found is that this comet's orbital characteristics best match those of thick disk or halo objects, not young disk objects. And when you look at the typical ages of thick disk stars, you find a population that's generally 7 to 14 billion years old. That's their 68% confidence interval, meaning there's a 2/3 chance that 3I Atlas falls within that age range. To put this in perspective, let's compare it to the comets we know from our solar system. Halley's Comet, probably the most famous comet in history, formed along with the rest of our solar system about 4.6 billion years ago. It's ancient by human standards, but 3I Atlas is potentially 3 times older. Think about what was happening 14 billion years ago. The universe was only about 800 million years old. The first stars were just beginning to die in spectacular supernovae seeding space with the heavy elements needed to make planets and eventually life. The Milky Way was still in its infancy, a chaotic, violent place where galaxies crashed together and merged. If 3I Atlas really is 14 billion years old, it might have formed in a completely different galaxy, one that later merged with what would become the Milky Way. Galaxy mergers were common in the early universe. Small galaxies crashed together their stars, and gas mixing their gravitational interactions, flinging objects every which way. 3I Atlas could be a refugee from one of those ancient collisions ejected from its birth system during the chaos and left to wander through the growing galaxy. But let's not get ahead of ourselves. That 7.6 to 14 billion year estimate has a lot of uncertainty. The researchers are careful to point out that this is based on statistical likelihood, not direct measurement. There's a 32% chance, roughly 1 in 3, that 3I Atlas falls outside that age range. It could be younger, perhaps only 5 or 6 billion years old. Or it could be even older, though that becomes increasingly unlikely as you push back toward the Big Bang itself. What we can say with more certainty is where 3I Atlas came from in terms of direction. When astronomers traced its trajectory backward through time, accounting for the sun's gravity and the comet's hyperbolic path, they found it approached our solar system from the direction of Sagittarius. That's a constellation you can see from Earth's southern hemisphere, and it happens to lie in the direction of our galaxy's center. Now, that doesn't mean 3I Atlas came from the galactic center itself. The galaxy is a three-dimensional structure, and we're viewing it from inside. When we look toward Sagittarius, we're looking through the galaxy's disk toward the central bulge and beyond. 3I Atlas could have come from anywhere along that line of sight. It could have originated from a star system in the inner galaxy, closer to the center where stars are more densely packed. Or it could have come from much farther away from a star on the opposite side of the galaxy, and we just happened to see it approaching from that direction based on the geometry of its orbit. What's particularly interesting is that radial velocity component, that U value of negative 51 kilometers per second. Remember, negative means it's moving away from the galactic center. So, as 3I Atlas orbits the Milky Way, it's currently on an outward leg of its journey, heading away from the crowded inner regions toward the sparse outer reaches. Combined with that high vertical velocity, we can picture this comet's orbital path, a giant tilted ellipse around the galactic center, diving up and down through the disk, sometimes plunging through the crowded central regions, other times climbing high into the sparse halo. Let me paint a picture of what 3I Atlas's journey might have looked like over billions of years. Imagine you could speed up time and watch the galaxy from outside. You'd see it slowly rotating, taking about 225 million years for a full revolution at the sun's distance, what's called a galactic year. But 3I Atlas isn't moving in a simple circle. Its orbit is eccentric and tilted. Sometimes it's down in the galactic disk, weaving between stars, occasionally passing through vast molecular clouds where new stars are being born. The radiation and stellar winds from massive young stars would sandblast its surface, perhaps stripping away some of its outer layers. Then it climbs, rising up out of the disk into the galactic halo, that vast spherical region of space where old stars drift in lonely isolation. Up here, the density of matter is incredibly low. 3I Atlas might go millions of years without passing anywhere near another star. The temperature of space is just a few degrees above absolute zero, and the comet is frozen solid, utterly dormant, a dark, invisible ice ball drifting through the void. Eventually, gravity brings it back down through the disk. Maybe it passes through a spiral arm, those regions of enhanced density where stars cluster more thickly. The increased density means a slightly higher chance of gravitational interactions, tiny tugs from passing stars that very gradually alter the comet's orbit over millions of years. Then it continues its journey, climbing back up on the other side, a cosmic yo-yo, eternally bouncing through the galaxy. How many times has 3I Atlas completed this cycle? If it's truly 14 billion years old, and each full orbit around the galaxy takes a few hundred million years, it's completed dozens of galactic orbits, maybe 50, maybe 100. Each orbit is slightly different because of those gravitational interactions, those tiny perturbations that accumulate over time. The orbit slowly evolves, precesses changes shape and orientation. And here's something that should make you pause in all that time through all those orbits 3I Atlas somehow avoided being destroyed. Comets are fragile things. They're not solid rock. They're mixtures of ice and dust, loosely bound together by gravity and frozen volatiles. When they get too close to a star, Thermal stress can crack them apart. We see this happen regularly with solar system comets. Just look at what happened to Comet Shoemaker-Levy 9, which broke into more than 20 pieces before crashing into Jupiter in 1994. 3I Atlas has survived billions of years of potential destruction. It never got captured by a star and forced into a tight orbit that would have vaporized it. It never suffered a direct collision with another object, which would have shattered it. It never passed so close to a star that tidal forces ripped it apart. It's either been incredibly lucky, or it's tougher than we think, or perhaps it started out much larger and has been slowly eroded down to its current size over the eons. Now, let's talk about that thick disk population, because this is where things get really interesting from a galactic archaeology perspective. The Milky Way's structure tells a story of its formation and evolution. The youngest component is the thin disk, where our sun lives a flattened region, just a few hundred light years thick, but about 100,000 light years across. This is where active star formation happens, where you find bright young stars and dense molecular clouds. Above and below the thin disk is the thick disk, a more puffed-up region extending perhaps 1,000 to 3,000 light years above and below the galactic plane. Stars in the thick disk are older, with ages typically exceeding 10 billion years. They have lower metallicities than thin disk stars, meaning they formed from more primordial material. And they have higher velocity dispersions, including those high vertical velocities we see in 3I Atlas. The thick disk is thought to have formed early in the galaxy's history through a combination of processes. Some thick disk stars might have been born in the disk itself, but were heated. Their orbits puffed up by gravitational interactions with satellite galaxies that merged with the Milky Way. Others might be the remnants of those satellite galaxies themselves, stars that were stripped away during the merger, and now orbit the Milky Way independently. If 3I Atlas belongs to the thick disk population, it's a fossil from this early violent epoch of galactic history. It formed when the galaxy was young and chaotic, when massive stars were being born and dying in rapid succession, when supermassive black holes were growing in galactic centers, when the cosmic environment was far more energetic and dangerous than it is today. Think about the implications. The material that makes up 3I Atlas, the ice and dust and rock, was formed from gas that condensed around a star billions of years ago. That gas had been enriched by earlier generations of supernovae, but not as enriched as the material in our solar system. The star it formed around is almost certainly dead now. Stars don't live for 14 billion years unless they're tiny red dwarfs with very low mass. If 3I Atlas formed around a sun-like star, that star burned out billions of years ago, swelling into a red giant and eventually shedding its outer layers to become a white dwarf. But 3I Atlas escaped. Somehow, early in that system's history, gravitational interactions between planets or close encounters with passing stars or some chaotic event flung this comet out into interstellar space. And it's been wandering ever since, orphaned homeless, drifting through the galaxy with no star to call its own. There's something profoundly melancholy about that, isn't there? This object has been alone in the dark for billions of years. It's outlived its birth star. It's outlived entire generations of stars. It's witnessed the galaxy transform from a young chaotic system into the mature spiral we see today. And all that time, it's been frozen dormant, dark and visible, drifting silently through space with no one to observe it, no one to know it exists. Until now. Until it happened to pass through our solar system in 2025, and we happened to be looking in the right direction, with the right instruments, at the right time. For a brief moment measured in months, this ancient wanderer is illuminated by our sun, warmed enough to sublimate some of its ice, creating that faint coma and tail that revealed its presence. We're studying it, learning from it, extracting every bit of information we can. And then it will fade back into darkness, continuing its eternal journey through the galaxy, and the next time it passes through someone's solar system, humanity might be long gone, Earth might be a barren rock, The sun might be a white dwarf, and whatever civilization discovers it next, we'll be dealing with a galaxy that looks very different than the one we know. But here's the beautiful thing right now. In this moment, 3i Atlas is giving us a gift. It's not just an astronomical curiosity, it's a direct physical sample from a different era of cosmic history. Every measurement we make, every spectrum we capture, every image we take is telling us something about conditions in the galaxy billions of years ago. The composition of its ice tells us about the chemistry of the star system where it formed. The structure of its nucleus, if we can resolve it, tells us about accretion processes in the early solar nebula around that long-dead star. The organic molecules we might detect in its coma tell us about the raw materials that existed in the early universe, the building blocks that eventually led to life on Earth and possibly elsewhere. And there's one more thing to consider, something that should make you think twice about our place in the cosmos. If 3i Atlas has been wandering for 14 billion years, if it's visited dozens or hundreds of star systems during its journey, then the odds are non-zero that it's passed by other planets, maybe even other planets with life. Maybe it flew through the outskirts of a solar system where an alien civilization looked up at the sky, saw this faint comet, and wondered where it came from, just as we're doing now. Maybe it passed by worlds where primitive life was just emerging from the oceans. Maybe it witnessed the birth of stars that have since died. We'll never know. The comet carries no record of these encounters. It's just ice and rock, frozen and inert. But it connects us in a tangible way to the wider galaxy. It's touched regions of space we'll never reach. It's witnessed epochs of time we can only imagine. And for this brief window, it's sharing its journey with us. Now, speaking of that journey we've talked about, where 3i Atlas came from and how long it's been traveling, but what about its actual passage through our solar system? Because this isn't just a flyby, this is a grand tour, a cosmic road trip through our planetary neighborhood. From its encounter with Mars to its close approach to Earth, from its swing past Jupiter to its eventual exit beyond Neptune's orbit, 3i Atlas is giving us a front row seat to watch an interstellar object navigate through the architecture of our home system. And that tour reveals just as much about us as it does about the visitor. Imagine planning a road trip across the United States. You'd map out your route, decide which cities to visit, calculate how long each leg of the journey would take. Now imagine that road trip, but the highway is 4.5 billion miles long. The speed limit is 152,000 miles per hour, and your vehicle is a frozen chunk of ice older than Earth. That's essentially what 3i Atlas is doing right now. It's on the ultimate cosmic road trip through our solar system, passing by planet spacecraft and moons in a carefully choreographed dance determined by gravity and geometry. But here's what makes this particular tour extraordinary. We're not just watching from the sidelines. We've positioned an entire fleet of spacecraft telescopes and observatories along the route, creating the most comprehensive observation campaign of an interstellar object in human history. 12 NASA missions alone have captured images of this visitor. Multiple space agencies coordinated their assets. Hundreds of ground telescopes tracked its path. This isn't just astronomy. This is humanity pulling out all the stops to study something we might never see again. If you're amazed by the coordination it takes to study a cosmic visitor at these scales, leave a like and subscribe, because we're witnessing history unfold in real time, and there's so much more to explore. Let's start with the timeline, because the precision here is remarkable. On October 29th, 2025, at exactly 11 for Universal Time, 3i's, Atlas reached perihelion, its closest approach to the Sun. At that moment, it was 1.36 astronomical units from our star, about 203 million kilometers, which places it between the orbits of Earth and Mars. That's actually a pretty safe distance. Unlike some comets that graze the Sun's atmosphere and get vaporized, 3i Atlas stayed well back, passing through a relatively benign region of space, where temperatures, while hot enough to sublimate ice, aren't extreme enough to cause catastrophic breakup. The choice of that particular distance tells us something about where this comet came from. Objects that form in the outer regions of planetary systems, beyond what's called the snow line, where water can freeze, tend to have orbits that keep them at moderate distances from their stars, even when ejected. If 3I Atlas had originated from very close to its parent star, it would likely have a different composition, more rock than ice. But the fact that it's clearly ice-rich and has a perihelion distance in this range suggests it formed in the outer regions of its birth system, similar to where comets in our Kuiper Belt reside. Now, just 5 days earlier, on October 3rd, 2025, something unprecedented happened. 3I Atlas passed within 30 million kilometers of Mars. That's about 19 million miles, which in space terms is remarkably close. For context, the Moon is only 384,000 kilometers from Earth, so 3I Atlas came nowhere near that intimate with Mars. But compared to how far apart objects usually are in space, this was a golden opportunity. NASA's Mars fleet went into action. The Mars Atmosphere and Volatile Evolution, mission MAVEN, which has been orbiting the red planet since 2014, turned its instruments toward the approaching visitor. MAVEN's ultraviolet spectrograph, designed to study Mars's upper atmosphere and how it interacts with the solar wind, is also perfect for observing comets. Ultraviolet light reveals hydrogen, the lightest and most abundant element in the universe, and comets produce huge clouds of hydrogen when water molecules in their ice get broken apart by solar radiation. The images MAVEN captured are stunning. They show a diffuse glow of hydrogen atoms surrounding the comet's nucleus, extending tens of thousands of kilometers into space. This hydrogen envelope is invisible to the human eye, but in ultraviolet, it lights up like a beacon. What's particularly clever is that MAVEN's instrument can distinguish between hydrogen from different sources based on velocity. The comet's hydrogen is moving at specific speeds as it streams away from the nucleus. Mars's own hydrogen from its thin atmosphere being stripped away by the solar wind moves at different speeds. And there's also interplanetary hydrogen, a background population of atoms drifting through the space between planets. By separating these populations, MAVEN could isolate the comet's contribution and study it in detail. But MAVEN wasn't alone. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter also observed 3I Atlas during this close approach. These spacecraft have different instruments, different capabilities. Mars Express carried out observations with its high-resolution stereo camera, capturing visible light images of the comet against the backdrop of space. ExoMars TGO, designed primarily to study trace gases in Mars's atmosphere that might indicate biological activity, turned its sensitive spectrometers toward the comet. And here's where it gets really interesting from a scientific perspective. Those observations from Mars orbit did something crucial. They dramatically improved our knowledge of 3I Atlas's trajectory. When you observe an object from multiple locations simultaneously, you get what's called parallax, the apparent shift in position due to viewing angle. From Earth, we see 3I Atlas from one perspective. From Mars orbit spacecraft, see it from a different angle. By combining these observations, astronomers could triangulate the comet's position with far greater accuracy than using Earth-based observations alone. The result? Scientists narrowed down the uncertainty in 3I Atlas's orbital path by a factor of 10. That might not sound dramatic, but in practical terms, it means the difference between knowing roughly where the comet will be in a year versus knowing precisely where it will be. This precision is crucial for planning future observations and for understanding the comet's true trajectory through the galaxy. It's like the difference between knowing someone lives in New York versus knowing their exact street address. Even more impressively, NASA's Perseverance rover, sitting on the surface of Mars in Jezero Crater, turned its Mastcam-Z instrument skyward and captured images of the comet. Think about that for a moment. We have a robot on another planet designed to search for signs of ancient microbial life in Martian rocks. Taking time out from its primary mission, to photograph an interstellar visitor passing overhead. This is the kind of flexibility and coordination that modern space exploration enables. Then came December 19th, 2025, the day 3I Atlas made its closest approach to Earth. At precisely 1:10 a.m. Eastern Standard Time, 6 UTC, the comet passed within 1.8 astronomical units of our planet. That's approximately 270 million kilometers, or 168 million miles. To put that in perspective, it's about 1.8 times the distance from Earth to the Sun. The comet never posed any threat to our planet. It didn't even come particularly close by astronomical standards, but it was close enough to be observable with moderate-sized amateur telescopes, close enough to appear as a faint, fuzzy patch in the constellation Leo, and close enough to trigger a massive observing campaign. Ground-based telescopes around the world had been tracking 3I Atlas for months leading up to this moment. The Hubble Space Telescope orbiting Earth captured detailed images showing the comet's nucleus and coma structure. These images revealed something fascinating. The comet appeared more active than expected for an object at its distance from the Sun. The coma was brighter, more extended, suggesting that 3I Atlas might have a composition slightly different from solar system comets, perhaps with more volatile ices that sublimate at lower temperatures. The James Webb Space Telescope, humanity's most powerful infrared observatory, also observed 3I Atlas. JWST's near-infrared spectrograph broke down the comet's light into its component wavelengths, creating a detailed chemical fingerprint. This data revealed the presence of specific molecules in the coma water: vapor carbon monoxide, carbon dioxide, methane. Each molecule has a unique spectral signature, and by measuring the relative abundances, scientists can infer the temperature and pressure conditions where the comet formed billions of years ago. But perhaps the most exciting observation came from an unexpected source: NASA's PUNCH mission, the polarimeter to unify the corona and heliosphere. PUNCH is designed to study the sun's corona and how solar wind flows through space. Its wide-field imagers can see faint structures invisible to most telescopes. When pointed at 3I Atlas, PUNCH revealed the comet's tail in exquisite detail. The images show a short elongation extending to the right of the nucleus plasma and dust being swept away by solar radiation and the solar wind. By tracking how this tail responds to changing solar wind conditions, scientists can learn about the interaction between interstellar material and our sun's influence. Now, we leap forward to March 15th, 2026. This is when 3I Atlas will make its closest approach to Jupiter, the solar system's giant. And this encounter is particularly intriguing because the comet will come within about 54 million kilometers of the gas giant, closer than it came to Earth. That's roughly 1/3 of an astronomical unit, close enough that Jupiter's immense gravity will noticeably perturb the comet's trajectory. Jupiter is, in many ways, the solar system's goalkeeper. Its massive gravity has been deflecting and capturing objects for billions of years. Some asteroids and comets get gravitationally bound to Jupiter, becoming temporary satellites before escaping or crashing into the planet. Others get their trajectories significantly altered, sometimes being ejected from the solar system entirely, sometimes being sent inward toward the sun. But 3I Atlas, with its extreme hyperbolic trajectory and enormous speed, won't be captured. Jupiter's gravity simply isn't strong enough to hold something moving this fast. The comet will swing past its path, bent slightly by the gravitational interaction, but it will continue on its way. What makes this encounter scientifically valuable is that NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, will have a grandstand seat. Juno's instruments are designed to study Jupiter's atmosphere, magnetic field, and interior structure, but they can also observe passing objects. While the comet will be too distant for detailed imaging, Juno might be able to detect its hydrogen envelope or study how the comet interacts with Jupiter's powerful magnetosphere, the vast bubble of magnetic field surrounding the planet. There's also a beautiful symmetry here that I find poetic. Jupiter has probably ejected billions of comets from our solar system over its 4.6 billion year history. It's one of the main mechanisms by which objects become interstellar wanderers. And now, here's 3I Atlas possibly ejected from another system by a giant planet, much like Jupiter, billions of years ago, passing by our Jupiter on its way through. It's like two chapters of the same cosmic story briefly intersecting. After Jupiter, the timeline becomes more spread out. In July 2026, 3I Atlas will cross Saturn's orbital distance, though the planet itself will be far from the comet's path. The geometry just doesn't work out for a close encounter. Saturn will be on the opposite side of the Sun, minding its own business, while the comet passes through empty space where Saturn's orbit is. The same situation applies for Uranus, whose orbital distance the comet will cross in April 2027, and Neptune in March 2028. This raises an interesting point about orbital mechanics that even many space enthusiasts misunderstand. When we say a comet crosses a planet's orbit, that doesn't mean it encounters the planet. The solar system is three-dimensional, and planets are constantly moving along their orbits. The odds of a randomly arriving object being at the same point in space as a planet at the same time are vanishingly small. It's like two cars on separate highways at different altitudes. They might cross over, under each other, geographically, but they never actually meet. The fact that 3I Atlas came reasonably close to Mars and will approach Jupiter is partly luck, partly geometry. The comet's trajectory happens to intersect those planets' orbital paths at times when the planets are relatively nearby. But even then, relatively nearby still means millions of kilometers of separation. By the time 3I Atlas crosses Neptune's orbit in March 2028, it will be moving at about 26 kilometers per second, relative to the Sun having slowed down as it climbed up out of the Sun's gravitational well. Remember, it was doing 68 kilometers per second at perihelion. That's a loss of about 42 kilometers per second, which corresponds to the Sun's escape velocity at that distance. But even at 26 km/s, it's still moving fast enough to escape. That's the hallmark of a hyperbolic trajectory. No matter how far out you go, the object always retains some velocity. It never slows to zero. It never stops. It just keeps going. And here's something to consider. Beyond Neptune's orbit lies the Kuiper Belt, a region of icy bodies extending from about 30 to 50 astronomical units from the Sun. Then beyond that is the scattered disk, reaching out to perhaps 100 AU. And beyond that is the Oort cloud, a theoretical sphere of comets extending halfway to the nearest star, perhaps 100,000 AU from the Sun. 3I Atlas will pass through all of these regions over the next few thousand years, gradually exiting our solar system's sphere of influence. Will it collide with anything out there? Almost certainly not. Space is vast beyond comprehension. Even the Oort cloud, despite containing trillions of objects, is so spread out that the average distance between objects is millions of kilometers. It's like throwing a grain of sand into the Sahara Desert and expecting it to hit another grain of sand. The odds are essentially zero. But here's what I find most remarkable about this entire solar system tour. In 1977, NASA launched Voyager 1 and Voyager 2 on what was called the Grand Tour, taking advantage of a rare planetary alignment to visit multiple outer planets. Those spacecraft visited Jupiter, Saturn, Uranus, and Neptune over the course of a decade, sending back revolutionary images and data. It was one of humanity's greatest achievements in space exploration. 3I Atlas is doing its own grand tour, except it's completely natural, completely unguided. No propulsion system, no navigation computers, no mission planners. Just gravity and momentum, the same forces that have been guiding its path for billions of years. And unlike Voyager, which was carefully designed to visit specific planets at specific times, 3I Atlas's tour is random chance. It happened to enter our solar system at an angle in time that brings it past Mars and Jupiter, a slightly different trajectory, and it might have passed through without coming near any planet at all. Yet, despite this randomness, we're learning more from 3i Atlas than we ever learned from the Voyager flybys of these same regions, at least in terms of understanding interstellar objects, because Voyager was looking outward studying the planets themselves. But with 3i Atlas, we're looking at the visitor using our planets and spacecraft as reference points, as vantage points for observation. We're turning the solar system itself into a giant observatory, with instruments scattered from Mars to the outer planets, all focused on understanding this single object. The coordination required is staggering. Mission planners had to schedule telescope time months in advance. Spacecraft had to be reoriented, sometimes interrupting primary science operations. International cooperation was essential, with NASA, ESA, JAXA, and other space agencies all contributing observations. Amateur astronomers shared data. Professional observatories coordinated their observations to avoid redundancy. It's a testament to how seriously the scientific community takes opportunities like this. Because here's the thing, we don't know when the next interstellar object will visit. It could be next year. It could be a decade from now. Statistical models suggest that we should detect one or two per year once we have better survey telescopes online, but there's no guarantee. And each one will be different with its own unique properties and trajectory. So, when an object like 3i Atlas comes along, giving us months of observation time and passing relatively close to multiple planets, we grab that opportunity with both hands and squeeze every bit of science we can out of it. But all this observation, all this data collection raises a question. What are we actually seeing when we look at 3i Atlas? What do these images and spectra and measurements tell us about the comet's physical nature? Because it's one thing to track its trajectory and study its orbit. It's another thing entirely to understand what this object actually is, what it's made of, how it behaves. And that's where the real detective work begins, where multiple wavelengths of light reveal secrets invisible to the human eye. Light is a liar. That's not poetic metaphor, it's scientific fact. When you look at something, whether it's a person across the room or a comet in space, you're only seeing a tiny sliver of the electromagnetic spectrum. Your eyes respond to wavelengths between about 400 and 700 nanometers, what we call visible light. But the universe communicates in radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. Every wavelength tells a different story, reveals different secrets, shows you things invisible to human perception. When astronomers pointed every available instrument at 3i Atlas, from ground-based telescopes to space observatories, they weren't just looking at one comet. They were looking at dozens of different versions of the same object, each wavelength peeling back another layer of mystery. In visible light, it appeared as a fuzzy green blob with a faint tail. In ultraviolet, it glowed with a massive hydrogen envelope. In infrared, its heat signature revealed molecular composition. And in X-rays, something completely unexpected happened, something never before seen from an interstellar visitor that forced scientists to reconsider what they thought they knew about how comets interact with their environment. If you're fascinated by how much invisible light reveals about the universe, give this a like. And subscribe, because we're about to see 3i Atlas in ways your eyes never could. And it's absolutely stunning. Let's start with what human eyes could theoretically see, though you'd need help. At its brightest, 3i Atlas reached about magnitude 11, which makes it invisible to the naked eye. For reference, the faintest stars you can see from a dark location on a moonless night are about magnitude 6. Each increase in magnitude represents a decrease in brightness by about 2.5 times. So magnitude 11 is roughly 100 times fainter than what your unaided eyes can detect. But with a decent pair of astronomy binoculars or a small backyard telescope, you could spot it if you knew where to look. Those who did observe it visually described seeing a small fuzzy patch of light, slightly elongated with a greenish tint. That green color is real and tells us something important. It comes from diatomic carbon C2, a molecule made of two carbon atoms bonded together. When sunlight strikes carbon compounds in the comet's ice, it breaks them apart through a process called photodissociation. Some of those fragments recombine into C2, which has a strong emission at a wavelength of 518 nanometers, right in the green part of the spectrum. This same process makes many comets appear greenish in photographs, though the effect is too subtle for most people to notice visually. But here's what's interesting. The intensity of that green emission tells astronomers about the comet's activity level and composition. A very green comet has lots of carbon-rich material sublimating from its surface. 3I's Atlas showed strong C2 emission, suggesting it's relatively rich in carbon compounds compared to some solar system comets. This matches what we'd expect from an object that formed in the outer regions of a planetary system, where carbon monoxide and other carbon-bearing molecules would have been abundant in the primordial disk. Now, let's jump to the other end of the spectrum to X-rays, because this is where things get really exciting. On November 28th and in early December in 2025, two X-ray observatories, XRISM and XLM Newton, observed 3I Atlas and detected something remarkable, a diffuse glow of X-ray emission surrounding the nucleus. This made 3I Atlas the first interstellar comet ever observed in X-ray light. Think about that for a moment. We've been observing comets for thousands of years. We've studied them with every type of telescope imaginable. But never before had we seen an interstellar visitor in X-rays. How do comets produce X-rays? It's not through radioactive decay or nuclear reactions. Comets are cold-dead objects. The mechanism is actually quite elegant. As the comet moves through space, it encounters the solar wind, that stream of charged particles constantly flowing out from the sun. The solar wind consists mostly of protons and electrons moving at hundreds of kilometers per second. When these high-energy particles collide with neutral atoms and molecules in the comet's coma, particularly oxygen and nitrogen, they can strip away electrons in a process called charge exchange. When a highly charged ion captures an electron from a neutral atom, the electron drops into a low-energy state and the ion releases the excess energy as an X-ray photon. It's like a tiny explosion of high-energy light every time this exchange happens. With trillions of these collisions occurring every second in the comet's extended coma, you get a detectable X-ray glow. The extent of this glow is enormous, stretching roughly 400,000 kilometers into space, about the distance from Earth to the Moon. That's how far the comet's influence extends, how far its sublimated gases spread before dispersing into the solar wind. What makes the X-ray observations of 3I Atlas particularly valuable is that they tell us about the interaction between interstellar material and our sun's particle environment. The intensity and spectrum of the X-rays depend on the composition of the coma gases and the energy of the solar wind particles. By analyzing the X-ray data, scientists can measure abundances of specific elements, particularly oxygen, carbon, and nitrogen, which are hard to measure in other wavelengths. This gives us insights into the chemical makeup of the material that formed around another star billions of years ago. Moving to ultraviolet, we've already talked about MAVEN's observations from Mars orbit, but there's more to the story. Ground-based ultraviolet observations and data from the Hubble Space Telescope revealed the full extent of 3I Atlas's hydrogen envelope. When water molecules sublimate from the comet's ice and get hit by solar ultraviolet radiation, they break apart into hydrogen and hydroxyl, OH. The hydrogen atoms are so light that they escape the comet's weak gravity, easily forming this huge cloud. Hubble's observations showed this cloud extending more than 1 million kilometers from the nucleus, creating an invisible but massive sphere of hydrogen gas that would be completely undetectable to human eyes. The beautiful thing about ultraviolet astronomy is that it reveals activity invisible in other wavelengths. You can have two comets that look identical in visible light, but in UV, one might show intense activity while the other appears dormant. This is because UV traces the sublimation of water ice directly, while visible light often shows dust and other materials that might not correlate perfectly with ice activity. For 3I Atlas, the UV observations confirmed what visible observations suggested. This is an active comet vigorously sublimating ice as it passes through the inner solar system. Now, let's talk about infrared. And this is where the James Webb Space Telescope becomes the star of the show. JWST observes primarily in infrared wavelengths, which are perfect for studying cool objects like comets. Infrared light penetrates dust that would block visible light, allowing us to see deeper into the coma and potentially glimpse the nucleus itself. It also reveals the thermal emission from the comet, showing us which parts are warmer and which are cooler, giving clues about rotation composition and internal structure. When JWST's near-infrared spectrograph analyzed 3I Atlas, it broke down the infrared light into its component wavelengths, creating what's called a spectrum. A spectrum is like a fingerprint. Every molecule absorbs and emits light at specific wavelengths determined by its quantum mechanical energy levels. Water vapor has a characteristic pattern of absorption lines. Carbon dioxide has a different pattern. Methane, ammonia, carbon monoxide, they all have unique signatures. By identifying these patterns in the spectrum, scientists can determine exactly what molecules are present in the coma and in what quantities. The preliminary results from JWST show water vapor as expected, but also significant amounts of carbon monoxide and carbon dioxide. The ratio of CO to water is particularly interesting because it tells us about the temperature conditions where the comet formed. Carbon monoxide freezes at much lower temperatures than water around 25 Kelvin compared to 273 Kelvin. A comet rich in CO must have formed in a very cold region of its parent system, probably in the outer reaches beyond where giant planets orbit similar to our Kuiper belt, but possibly even colder. There's also tentative evidence for more complex organic molecules, carbon-based compounds that could include things like formaldehyde methanol or even amino acids. This is where it gets really exciting from an astrobiology perspective. Comets are thought to have delivered much of Earth's water, and possibly the organic building blocks necessary for life. If interstellar comets contain similar chemistry to solar system comets, it suggests that the ingredients for life might be universal seeded throughout the galaxy wherever comets form. But here's something that surprised scientists. 3I Atlas appears brighter than expected, based on models. When you know an object's distance from both the Sun and Earth, you can predict how bright it should appear based on its size and how reflective its surface is. 3I Atlas is brighter than those predictions suggest. There are several possible explanations. Maybe the nucleus is larger than estimated. Maybe the surface is more reflective, perhaps covered in fresh ice, rather than the dark, dusty crust that covers many solar system comets. Or maybe it's more active than typical sublimating ice at a higher rate and producing more dust and gas that scatter sunlight. The most likely explanation is that interstellar comets, having spent billions of years in the deep cold of space far from any star, accumulate a thick layer of extremely volatile ices on their surface materials that would sublimate quickly in the inner solar system but persist in interstellar space. When such a comet enters a solar system and begins to warm up, these super volatile ices sublimate, explosively creating enhanced activity. Solar system comets, by contrast, have already passed by the Sun dozens or hundreds of times. They have lost most of their volatile ices. They're old, weathered, covered in a dark lag deposit of dust and organics left behind as the ice sublimates. This brings us to the visible light observations in more detail, particularly the structure of the coma and tail. Professional observatories equipped with advanced CCD cameras captured stunning images showing 3I's Atlas with multiple tail structures. There's the dust tail made of solid particles pushed away from the nucleus by radiation pressure light itself, exerting force on the tiny grains. This tail curves gently following the comet's orbital path, because the dust particles maintain some of the comet's original velocity even as they're pushed by sunlight. Then there's the ion tail or plasma tail made of charged gas molecules. These molecules are ionized by solar ultraviolet light, meaning electrons get stripped away, leaving positively charged ions. The solar wind, with its embedded magnetic field, then sweeps these ions straight back away from the sun at high speed. Ion tails always point directly away from the sun, regardless of the comet's direction of motion, and they can change rapidly in response to fluctuations in the solar wind. When a gust of solar wind hits the comet, you can sometimes see the ion tail disconnect entirely, breaking off and forming a new tail. It's like watching the comet's atmosphere being ripped away in real time. Detailed images from the Gemini Observatory using its multi-object spectrograph on Gemini North in Hawaii revealed the fine structure of 3I Atlas's coma. They showed Jet's narrow streams of gas and dust emanating from specific regions on the nucleus. These jets form because comets don't sublimate uniformly over their entire surface. Some areas are more icy, some more dusty. Some areas face the sun, and heat up, others are in shadow and stay cold. As the nucleus rotates, different regions turn toward the sun, creating jets that spiral outward as the rotation carries the active region around. By tracking these jets over multiple nights and measuring how they change, astronomers can determine the comet's rotation period, how fast it's spinning. For 3I Atlas, the rotation period appears to be around 10 hours, meaning it completes one full spin roughly every 10 hours. That's actually pretty fast for a comet. Some rotate every few hours, others take days. The rotation rate depends on the object's size, shape, and history of outgassing activity, which can create torques that spin the nucleus up or slow it down over time. Now, here's something that really drives home the power of multi-wavelength astronomy. In visible light, you see the dust and the C2 emission, the green fuzzy glow. In ultraviolet, you see the hydrogen envelope vastly larger. In infrared, you detect heat and molecular composition. In X-rays, you witness the collision between the solar wind and cometary gases. Each wavelength is showing you a different physical process, a different aspect of the same object. It's like having multiple witnesses to a crime, each one seeing the event from a different angle and reporting different details. Only by combining all their testimonies do you get the complete picture. And we haven't even mentioned radio observations yet. Radio telescopes can detect molecules that don't emit strongly in other wavelengths. Hydroxyl OH, for example, emits at a wavelength of 18 centimeters right in the radio part of the spectrum. By measuring OH emission, astronomers can calculate the water production rate of the comet. How many kilograms of water are sublimating every second for 3I Atlas? At its peak activity, estimates suggest it was releasing roughly 100 kilograms of water per second. That might not sound like much, but multiply it out over weeks and months, and you're talking about millions of kilograms of mass lost to space. There's one more observation I need to mention because it's so remarkably poetic. The Stereo A spacecraft, which monitors the sun from a position offset from Earth, captured images of 3I Atlas as a time-lapse movie. Because stereo continuously images a wide field of view around the sun, you can see the comet moving against the background stars over days and weeks. It's mesmerizing watching this tiny speck of light, this visitor from another star, drift through our solar system. The stars appear as streaks because of stereo's imaging mode, but the comet moves differently, following its hyperbolic path here and then gone. What strikes me most about all these observations is the diversity of tools we brought to bear on a single object. This represents decades of investment in space infrastructure, ground telescopes, orbital observatories, planetary missions. None of these instruments was built specifically to study interstellar comets. Hubble was launched in 1990 to study galaxies and stars. JWST was designed for deep cosmology and exoplanet atmospheres. MAVEN studies Mars's atmosphere. But when an opportunity like 3i Atlas appears, we can repurpose all these assets, turn them toward a common target, and collectively learn things no single instrument could discover alone. Yet, despite all this observational firepower, despite images in every wavelength from radio to X-ray, despite spectra and photometry and astrometry and spectropolarimetry, we still can't answer some basic questions. We don't know the exact size of the nucleus. Estimates range from a few hundred meters to perhaps a kilometer or more. We don't know its exact composition, only the major constituents. We don't know its density, its internal structure, whether it's a solid chunk of ice or a loose rubble pile held together by weak gravity. These limitations aren't failures. They're reminders that even with all our technology, even with humanity's most sophisticated scientific instruments, all working together, nature still keeps secrets. And maybe that's okay. Maybe the mystery is part of the beauty. Because while we gathered all this data, while we learned unprecedented details about an interstellar visitor, something else was happening in parallel. Something unexpected and honestly quite strange. People were asking questions that had nothing to do with science. They were proposing explanations that didn't involve ice or rock or natural processes. They were wondering if perhaps we were looking at something artificial, something designed, something sent by intelligence from the stars. And that conversation, as we're about to explore, reveals just as much about humanity as it does about the cosmos. For 6 months, from the moment of its discovery in July 2025 through its close approach to Earth in December, one question dominated social media, online forums, and even casual conversations at parties. Is 3i Atlas actually an alien spacecraft? Not could it be? Or what if it were? But stated as a genuine possibility that deserves serious consideration. YouTube videos with millions of views analyzed its trajectory for signs of propulsion. Twitter threads dissected every NASA press release looking for hidden admissions. News articles asked scientists to respond to the theory, legitimizing it through coverage. Even respected journalists prefaced their questions with, "I know this sounds crazy, but..." And here's what's fascinating. This wasn't limited to conspiracy theorists or fringe groups. Educated, scientifically literate people were asking this question. The speculation went so viral that NASA felt compelled to release an official statement in November, explicitly stating that 3i Atlas is a comet, not a spacecraft. But the statement didn't stop the speculation. If anything, it fueled it. So, let's talk about why this happened, what it reveals about human psychology, and most importantly, what the actual science tells us about distinguishing natural objects from artificial ones. If you appreciate the difference between healthy skepticism and wild speculation, hit that like button. And subscribe, because separating signal from noise in the information age is maybe the most important skill we can develop. Let's start with the obvious question. Why did the alien spacecraft theory gain so much traction with 3i Atlas when it didn't with 2i Borisov? This is actually revealing in itself. Borisov looked exactly like a comet should look. It had a bright coma, a visible tail, all the classic cometary features. Nobody seriously suggested it was artificial because it behaved naturally. But 3i Atlas had some unusual characteristics that, when presented without proper context, could seem suspicious to non-experts. It brightened unexpectedly as it approached the sun, more than models predicted. Its speed was extreme, faster than any previous interstellar object. Its trajectory seemed almost perfectly aligned with the ecliptic plane, the disk in which planets orbit, which some interpreted as evidence of intelligent navigation. And perhaps most significantly, it came just 6 years after Oumuamua, which had sparked its own alien technology debate due to its bizarre elongated shape and anomalous acceleration. The Oumuamua controversy looms large over this entire discussion, so we need to address it directly. When that object was discovered in 2017, its properties were genuinely puzzling. The extreme elongation with a length-to-width ratio of at least 5:1 and possibly as high as 10:1 was unlike any natural object we'd seen. The fact that it showed no cometary activity, no coma or tail, yet still exhibited non-gravitational acceleration, violated our understanding of how objects behave. Something was pushing it, but we couldn't see what. Harvard astronomer Avi Loeb, chair of the astronomy department at one of the world's most prestigious universities, proposed in a peer-reviewed paper that Oumuamua could be a light sail, a thin reflective sheet pushed through space by radiation's pressure from stars, and that it might be of artificial origin. The media exploded. Harvard scientist says aliens became the headline, though Loeb's actual paper was far more nuanced, presenting this as one hypothesis among several and calling for more data. Most astronomers disagreed strongly with Loeb's interpretation. They proposed natural explanations. Maybe Oumuamua was outgassing hydrogen, which would be invisible but could still produce thrust. Maybe it was made of nitrogen ice from a Pluto-like world, which would explain both its reflectivity and behavior. Maybe our models of how such objects should look were simply wrong based on limited data from solar system objects. The debate became heated, sometimes personal, and it left a residue in the public consciousness, the idea that interstellar objects might be alien probes scanning the galaxy for life. So, when 3I Atlas appeared, the groundwork had been laid. People were primed to ask the alien question. And social media algorithms designed to maximize engagement rapidly amplified the most sensational interpretations. A post saying, "Scientists discover new comet," gets modest engagement. A post saying, "Is this interstellar visitor actually an alien spacecraft?" goes viral. The algorithm sees high engagement and pushes the content to more users. More users engage, often arguing in comments, which the algorithm interprets as valuable interaction. The cycle feeds itself. But here's what I find most troubling about this phenomenon. It reveals a fundamental misunderstanding of how science works. Science isn't about proving things definitively. It's about building models that best fit the available data while making the fewest assumptions. When we say 3I Atlas is a comet, we're not claiming absolute certainty. We're saying that the comet hypothesis explains all observed properties using only well-understood natural processes, while the spacecraft hypothesis requires assumptions about alien technology, motivations, and capabilities that we have zero evidence for. This is where we need to talk about Occam's razor, though I hesitate to invoke it because it's often misunderstood. Occam's razor doesn't say the simplest explanation is always correct. It says that when multiple hypotheses explain the data equally well, prefer the one that makes the fewest assumptions. The key phrase is equally well. If the natural explanation fails to account for observations, while the exotic explanation succeeds, then Occam's razor doesn't apply. You go with what works. So, let's examine the evidence systematically. What does 3I Atlas do that comets do? It has a coma. Multiple independent observations from professional observatories confirmed a diffuse cloud of gas and dust surrounding the nucleus. It has a tail, both dust and ion components visible in images from multiple wavelengths. It brightens as it approaches the sun, consistent with increasing sublimation of ice due to solar heating. Its spectrum shows emission lines from molecules like C2CNOH and water vapor, exactly what we expect from sublimating cometary ice. Its X-ray emission matches the charge exchange mechanism seen in other comets. Every single observation is consistent with a natural comet. What does it do that comets don't do? Nothing. Absolutely nothing. Yes, it's brighter than initial models predicted, but models are approximations based on assumptions about size, composition, and albedo that we can't measure directly. Comets frequently surprise us by being brighter or fainter than expected. That's not anomalous. That's normal variability. Yes, its speed is extreme, but we've explained that through orbital mechanics and its ancient origins. High eccentricity produces high velocity, There's no mystery there. What about that alignment with the ecliptic plane that some pointed to as suspicious? This is a perfect example of how a little knowledge can be misleading. Three eyes, he sighs. Atlas's trajectory is inclined at 175 degrees to the ecliptic, which sounds close to 180 degrees, a perfect retrograde orbit in the ecliptic plane. Some interpreted this as evidence the comet was deliberately aiming for the planetary disk. But 175 degrees means the trajectory is tilted 5 degrees from the ecliptic. And in astronomy, that's not particularly remarkable. Thousands of objects have similar inclinations. It's well within the range of random chance. The ecliptic isn't a razor-thin plane. It's a region several degrees thick containing most of the solar system's matter. An object coming from a random direction has a decent probability of passing through it. Moreover, and this is crucial, if you were an alien civilization sending a probe to study a solar system, would you really aim it through the planetary plane? That's the most dangerous trajectory possible. The plane is where most of the debris is, where collision risks are highest. A genuinely intelligently designed probe would probably approach from above or below the ecliptic, where space is cleaner and observation opportunities are better. The fact that 3i Atlas passes through the ecliptic actually argues against the spacecraft hypothesis. Now, let's talk about propulsion, because this was a major point of speculation. Several people claim to have detected changes in 3i Atlas's trajectory inconsistent with gravity alone, suggesting it was maneuvering. These claims circulated widely online before being debunked. When professional astronomers carefully analyzed the data, accounting for observational uncertainties and the perturbations from planetary gravity, they found the trajectory matched gravitational predictions perfectly. There was no evidence of thrust, no unexplained acceleration, nothing anomalous. This is a great example of the difference between amateur analysis and professional astronomy, modern astrometry. The science of measuring positions of celestial objects is extraordinarily precise, but also extraordinarily complex. You need to account for the motion of the observer on Earth's surface, Earth's rotation and orbit around the Sun, the refraction of light through Earth's atmosphere, the gravitational effects of all the planets, the relativistic bending of space-time near the Sun, and dozens of other subtle effects. Get any of these wrong, and you'll measure false accelerations that don't exist. Professional astronomers spend years learning how to do this correctly. When amateurs skip those steps and find anomalies, it's usually because they made a mistake, not because they discovered something real. But let's steelman the alien hypothesis for a moment. Let's assume, purely for argument's sake, that an advanced civilization wanted to send probes to explore the galaxy. What would those probes look like? They'd probably be small to minimize mass and energy requirements. They'd be autonomous, since radio communication across light years introduces years or decades of delay. They'd probably be dormant most of the time, activating only when approaching a star system to conserve power. They might use light sails for propulsion, slowly accelerating over centuries using starlight. And crucially, they'd probably do everything possible to avoid detection, because you don't know if the civilizations you encounter will be friendly or hostile. Does 3i Atlas match this profile? Not even remotely. It's large enough to show cometary activity, meaning it's at least hundreds of meters across. That's enormous for a spacecraft. It's bright, visible, releasing clouds of gas and dust that draw attention. Its trajectory doesn't involve any complex maneuvers to visit multiple planets or enter orbit around the Sun. It's just passing through in a straight line. If this is a probe, it's the worst designed probe imaginable, like trying to spy on a military base by driving past the front gate in a neon pink car with sirens blaring. Here's another angle to consider: the sheer improbability of detection. If alien civilizations are sending probes through the galaxy, those probes would be vastly outnumbered by natural interstellar objects. For every artificial probe, there might be trillions of comets and asteroids ejected from planetary systems. The odds that one of the first three interstellar objects we detect would happen to be artificial is astronomically small. It would be like finding a needle in a haystack, except the haystack is the size of the galaxy and contains only a handful of needles. But here's what I think really drives the alien speculation, and it's something we need to be honest about. People want it to be true. The discovery of extraterrestrial intelligence would be the most significant event in human history. It would answer the profound question of whether we're alone in the universe. It would give meaning and context to our existence in ways that transcend science. So, when an ambiguous situation arises, when an object shows properties we don't immediately understand, there's a strong psychological pull toward the exotic explanation. Hope and wonder and a deep yearning for cosmic connection all push us in that direction. I understand that pull. I feel it too. The idea that 3i Atlas could be a visitor from an alien civilization is thrilling. It would be the most exciting discovery of our lifetimes. But science doesn't work through wishful thinking. It works through evidence, and the evidence overwhelmingly supports a natural explanation. Not sort of supports, not mostly supports. Overwhelmingly supports. Every test we can perform, every observation we make, every spectrum we analyze, all point to the same conclusion. This is a comet, a remarkable comet, yes. An ancient comet from another star system, absolutely, but a comet nonetheless. The real lesson here isn't about 3i Atlas. It's about critical thinking in the age of viral misinformation. We live in an era where anyone can publish anything online and reach millions of people within hours. The old gatekeepers, traditional media, and academic institutions no longer have a monopoly on information distribution. That's largely positive. It democratizes knowledge and enables valuable citizen science. But it also means we're flooded with claims of varying quality, and we need to develop better filters. Here's a framework I use when evaluating extraordinary claims, and I encourage you to adopt something similar. First, ask who is making the claim. Are they an expert in the relevant field? Do they have a track record of accurate analysis? What's their motivation? Second, ask, what's the quality of the evidence? Is it based on rigorous analysis or quick speculation? Has it been peer-reviewed? Can other experts replicate the findings? Third, ask, what do the majority of experts think? Consensus isn't always right. But when 99% of astronomers agree on something, that's usually because the evidence is strong. Fourth, ask what would it take to convince you otherwise. If no amount of evidence could change your mind, you're not engaging in science. You're engaged in faith. Applying this framework to 3i Atlas makes the situation clear. The people most qualified to evaluate it, professional astronomers with decades of experience, overwhelmingly agree it's a comet. The evidence supporting that conclusion is extensive and has been published in peer-reviewed journals. The spacecraft hypothesis has not been published in any reputable scientific venue because it doesn't meet basic evidentiary standards. And the proponents of the spacecraft hypothesis often shift their arguments when faced with contradictory evidence, a classic sign of motivated reasoning, rather than genuine inquiry. Does this mean we should never consider exotic explanations? Absolutely not. Science progresses by challenging assumptions and exploring alternatives. Loeb's willingness to seriously propose the light sail hypothesis for Oumuamua, regardless of whether he's ultimately correct, is valuable because it forces us to articulate exactly why we prefer natural explanations. It makes us examine our assumptions. But there's a crucial difference between proposing a hypothesis for scientific discussion and claiming that hypothesis is likely true despite lack of supporting evidence. The first is healthy skepticism. The second is pseudoscience. And here's something that should give us all pause. The alien spacecraft theory for 3i Atlas is harmless, just fun speculation. But the same psychological mechanisms that make it appealing drive belief in genuinely dangerous misinformation about vaccines, climate change, elections, and public health. The inability to distinguish between plausible scientific hypotheses and baseless speculation has real consequences. Learning to think critically about something low stakes like an interstellar comet is practice for the high stakes situations where getting it right actually matters. What I hope you take away from this isn't cynicism, it's nuance. The universe is full of genuine mysteries that should spark our imagination and drive our curiosity. But not every mystery requires an exotic solution. Sometimes, and in fact, most of the time, the natural explanation is correct. And honestly, natural phenomena are often more amazing than any alien technology we could imagine. The fact that 3I Atlas is a natural comet, a frozen remnant from a star system billions of years old, traveling through space since before Earth existed, passing through our solar system by pure chance is already extraordinary. It doesn't need to be artificial to be awe-inspiring. Now, while the speculation swirled online and people debated whether we were looking at ice or intelligence, something else was happening quietly in the background. Scientists and engineers were coordinating planning, working together across institutions and nations to extract every possible bit of knowledge from this fleeting opportunity. Because whether it's a comet or a spacecraft, whether it's natural or artificial, 3I Atlas represents something unprecedented, a chance to study material from another star system. And that coordination, that international scientific cooperation, reveals something beautiful about humanity that the alien speculation missed entirely. On a quiet morning in Geneva, representatives from 84 different countries sat in a conference room discussing a frozen ball of ice 200 million kilometers away. Not diplomats negotiating treaties, not politicians debating policy. Scientists and engineers speaking a common language of orbital mechanics and spectroscopy, coordinating the most comprehensive observation campaign ever directed at a single astronomical object. This is the International Asteroid Warning Network, IAWN, a United Nations sanctioned collaboration that most people have never heard of, but that might one day save civilization from extinction. ION was designed to track potentially hazardous asteroids that could strike Earth. But when 3I Atlas appeared, they made a remarkable decision. They would use this interstellar visitor as a test case, a rehearsal for future encounters with objects we've never seen before. They would develop new tracking techniques, test communication protocols, validate prediction models, and coordinate observations across continents and time zones. And in doing so, they would demonstrate something profound, that when confronted with cosmic mysteries, humanity can set aside borders and politics and work together toward understanding. The results of their coordinated effort will be published in 2026, but the implications extend far beyond one comet. If you believe the best of humanity emerges when we work together on something bigger than ourselves, show some love with a like. And subscribe, because the story of how we explore space is really the story of cooperation overcoming division. Let's start with what IAWN actually is, because this organization deserves far more recognition than it receives. Established in 2014 under the auspices of the United Nations Committee on the Peaceful Uses of Outer Space, IAWN brings together observatories, space agencies, research institutions, and amateur astronomy groups from around the world, with a single mission: identify and track near-Earth objects that could potentially impact our planet and provide early warning if a collision is imminent. It's planetary defense, but not the movie version with nuclear weapons and heroic sacrifices. The real version involves patient astronomers scanning the sky night after night, mathematicians calculating orbits with extraordinary precision, and international cooperation to ensure no potential threat slips through the cracks. The network includes some of the world's most powerful telescopes: Pan-STARRS in Hawaii, which discovered Oumuamua, the Catalina Sky Survey in Arizona, the European Space Agency's optical ground stations, Russia's master network of robotic telescopes, Australia's Siding Spring Observatory, Japan's Subaru Telescope, China's Purple Mountain Observatory, more than 80 participating organizations spanning every inhabited continent, all sharing data in real time, all contributing to a comprehensive map of objects that cross Earth's orbit. But here's what makes IAWN remarkable. It's not just about Earth defense. It's a framework for rapid response to any unusual astronomical event. When something interesting appears, whether it's a potentially hazardous asteroid or an interstellar visitor, IAWN can mobilize global resources within hours. And that's exactly what happened with 3I Atlas. Within days of the discovery announcement, the network activated, and observatories around the world began coordinating their observations. The stated goal was ambitious use, 3I Atlas, as a test case for tracking future interstellar objects, and develop methodologies that could someday enable sending a spacecraft to intercept one. Think about that for a moment. We've sent probes to every planet in the solar system. We have landed on comets and asteroids, but we've never intercepted an object from interstellar space. The technical challenges are enormous, and 3I Atlas gave us a chance to work through them with a real target. The first challenge is detection and characterization. How quickly can we identify an interstellar object, calculate its trajectory, and determine whether it's scientifically interesting enough to warrant a spacecraft mission? With 3I Atlas, we had the advantage of pre-discovery observations going back several weeks, but ideally we'd want to detect such objects months or even years in advance to allow time for mission planning and spacecraft construction. ION researchers developed new algorithms for sifting through telescope data, looking for objects with hyperbolic trajectories. Remember, most objects in our solar system have elliptical orbits. Anything with eccentricity above 1.0 is immediately suspicious and deserves rapid follow-up, but false positives are common. Observational errors can make an object appear to have higher eccentricity than it actually does. You need multiple observations from different locations to confirm the trajectory is genuinely hyperbolic. With 3I Atlas, the network demonstrated they could confirm interstellar origin within 48 hours of discovery. That's remarkable when you consider the complexity involved. Multiple observatories need to observe the object, reduce their data, calculate preliminary orbits, compare results, and reach consensus. 2 days from discovery to confirmation represents a dramatic improvement over Oumuamua, which took weeks to confirm, and it's fast enough to enable time-critical science. The second challenge is trajectory refinement. Knowing an object is interstellar is one thing. Knowing precisely where it's going and when it will be at specific locations is another. This is where the ExoMars Trace Gas Orbiter's contribution becomes particularly important. By observing 3I Atlas from Mars' orbit and comparing those observations with Earth-based measurements, scientists achieved that tenfold improvement in trajectory precision we mentioned earlier. This technique, called parallax ranging, will be crucial for any future intercept mission. Here's why. If you want to send a spacecraft to rendezvous with an interstellar object, you need to know where that object will be months or years in the future with extraordinary accuracy. A small error in the calculated trajectory compounds over time. Miss by a few kilometers in your initial position, estimate, and by the time you arrive at the predicted intercept point, you could be millions of kilometers away. The object is moving at tens of kilometers per second. You get one chance. You can't circle back for another try. ION's work with 3I Atlas demonstrated that by combining observations from Earth-Mars orbit and potentially other locations like the Moon or L2 Lagrange point, we can achieve the precision necessary for intercept mission planning. But precision alone isn't enough. You also need long lead time, which brings us to the third challenge, rapid trajectory prediction. When 3I Atlas was first detected, astronomers had only a few data points. Calculating a reliable orbit from limited data is mathematically challenging. The orbit determination software used by the Minor Planet Center employs sophisticated algorithms that can handle this, but there's always uncertainty. With each new observation, the uncertainty decreases, but in those first few days, the predicted trajectory can change significantly as better data comes in. For a spacecraft intercept mission, you'd need to commit to a launch trajectory based on early orbital predictions before you have perfect data. IAWN used 3I Atlas to test how well their early predictions matched the eventually refined orbit. The results were encouraging. Within a week of discovery, their predicted trajectory was accurate enough that a spacecraft launched toward the predicted intercept point would have arrived within range for final course corrections. Now, let's talk about the European Space Agency's contributions, because ESA has been particularly forward-thinking about interstellar objects. Beyond the Mars observations, we've discussed ESA's JUICE mission, the Jupiter Icy Moons explorer currently en route to the Jovian system, also observed 3I Atlas in November 2025. JUICE is carrying a suite of cameras and spectrometers designed to study Jupiter's moons, but these instruments work equally well for observing passing comets. The really interesting part is that JUICE captured images showing 3I Atlas in an active state, with visible coma and tail, despite being far from Earth and communicating through a low-bandwidth antenna. Due to JUICE's position on the far side of the Sun, from Earth transmitting data is slow and difficult. The fact that they prioritized observations of 3I Atlas and succeeded in returning usable scientific data demonstrates ESA's commitment to studying these objects. And this brings us to Comet Interceptor, one of the most exciting missions in development. Selected by ESA in 2019 and scheduled to launch in 2029, Comet Interceptor is designed to visit a pristine Comet 1 that's either entering the inner solar system for the first time or in the mission's wildest dreams, an interstellar object passing through. The mission architecture is clever rather than launching directly to a specific target. Comet Interceptor will park itself at the Sun-Earth L2 Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth, and wait there for a suitable target to be discovered. Once a target is identified, Comet Interceptor will leave L2 and intercept the object as it passes through the inner solar system. The spacecraft consists of 3 separate probes that will split apart before encounter, allowing simultaneous observations from multiple angles. It's like having 3 spacecraft for the price of one, maximizing the scientific return from a single brief flyby. Here's the beautiful thing: Comet Interceptor could potentially target an interstellar object if one is discovered with the right trajectory. The mission is designed to handle objects with high relative velocities up to about 70 kilometers per second, which is right in the range of what we've seen from interstellar visitors. It would require extraordinary luck, the right object arriving at the right time, but it's possible. And even if Comet Interceptor never encounters an interstellar object, the technologies and techniques developed for this mission will inform future dedicated interstellar intercept missions. Speaking of future missions, the lessons learned from observing 3I Atlas are already influencing mission concepts at NASA, ESA, and other space agencies. One proposal gaining traction is a rapid response spacecraft kept in a state of high readiness, fueled and prepared to launch on short notice when an interstellar object is detected. The spacecraft would carry cameras, spectrometers, maybe even a penetrator probe that could impact the object and analyze the ejected material. The engineering challenges are substantial. You need a spacecraft that can remain in storage for years, without degradation, ready to launch within weeks. You need propulsion capable of matching velocity with an object moving at tens of kilometers per second. You need instruments robust enough to survive a high-speed flyby through a dusty coma. And you need funding approval for a mission that might not launch for a decade or more, if ever. That's a tough sell to budget committees. But 3-Eye Atlas has helped make the case. The unprecedented international observation campaign demonstrated the scientific value of studying these objects. The detailed data collected answered some questions while raising new ones that can only be addressed with in situ measurements. And the public interest, even if some of it veered into alien speculation, showed that interstellar visitors capture imagination in ways that routine asteroid studies don't. There's also a planetary defense angle that's harder to dismiss. Suppose an interstellar object were discovered on a collision course with Earth. It's incredibly unlikely the odds are infinitesimal, but not zero. How would we respond? Could we deflect it using the same techniques we're developing for near-Earth asteroids? Or would its extreme velocity and uncertain composition make those techniques ineffective? IAWN's work with 3-Eye Atlas included modeling exercises exploring exactly these scenarios. The model suggests that deflecting an interstellar impactor would be extraordinarily difficult. The high velocity means the object spends very little time within range of Earth-launched interceptors. You'd have maybe weeks of warning, not the years or decades you'd have for a typical asteroid threat. And the deflection techniques being developed like kinetic impactors or gravity tractors work best when you have time to apply small forces that accumulate over months or years. Against a fast-moving interstellar object, you'd need enormous forces applied quickly, probably requiring nuclear explosives, and even then success wouldn't be guaranteed. Fortunately, the actual risk is vanishingly small. The galaxy is vast. Interstellar objects are rare compared to solar system objects, and the odds of one randomly hitting Earth are comparable to winning the lottery multiple times in a row. But the exercise of working through the scenario helps us prepare for more plausible threats and tests our international cooperation frameworks. And that cooperation is perhaps the most important outcome of the 3-Eye Atlas campaign. Astronomy has always been an international endeavor. The sky doesn't respect borders. Objects discovered by one observatory need to be confirmed by others. Data sharing has been the norm for centuries. But 3-Eye Atlas represented a new level of coordination, with space agencies directing planetary missions to observe the same target ground telescopes, coordinating to provide continuous coverage as Earth rotates, and amateur astronomers contributing observations that fill gaps in the professional data. This is something worth celebrating as you drift off tonight, the capacity for humans to work together when confronted with something larger than ourselves. During the 6 months of intensive 3-Eye Atlas observations, wars were being fought, political divisions were deepening, economic tensions were rising. Yet scientists from nations with challenging diplomatic relationships collaborated seamlessly. Russian astronomers shared data with American colleagues. Chinese observatories coordinated with European ones. It wasn't utopian. There were disagreements about methodology and interpretation. But the disagreements were scientific, not political. The shared goal of understanding this cosmic visitor transcended the conflicts that divide us. There's a lesson there about human nature. We're capable of both amazing cooperation and terrible conflict. Which tendency dominates depends on the context we create. When we frame challenges as zero-sum competitions where one side's gain requires another's loss, conflict is inevitable. But when we frame challenges as shared problems requiring collective effort, cooperation emerges naturally. Space exploration at its best creates that cooperative context. The universe is so vast, the challenges so immense that no nation can tackle them alone. Success requires sharing knowledge, coordinating efforts, building on each other's work. And the work continues. The observations of 3-Eye Atlas will be analyzed for years, probably decades. Each wavelength of data, each spectrum, each time-resolved measurement contains information we haven't fully extracted yet. Students who are in elementary school now will write PhD dissertations analyzing this data. Techniques that don't exist yet will reveal insights we can't anticipate. That's how science works. The initial observations are just the beginning. The real understanding emerges gradually as researchers worldwide contribute their expertise and creativity to interpreting what we've seen. But even as we continue to analyze 3I Atlas, even as we plan missions to intercept future interstellar visitors, even as we marvel at the international cooperation that made these observations possible, there's a bigger question we haven't addressed. What happens next? Not just to 3I Atlas, which will fade into the darkness beyond Neptune and disappear from our instruments, but to our understanding of interstellar objects in general, to our exploration of the cosmos, to our place in the universe. Because this visitor, remarkable as it is just one data point. We need to step back, look at the bigger picture, and ask ourselves what all of this means for the future of astronomy and our species' journey into space. That's where we're headed, to the implications, the possibilities, the questions that remain unanswered, and the profound ways that objects like 3I Atlas are reshaping how we see ourselves and our cosmic neighborhood. Picture 3I Atlas right now at this very moment. It's already beyond Earth's orbit, racing outward at speeds that would cross the United States in less than a minute. The sun behind it grows smaller each day, fading from a brilliant disk to just another bright star among countless others. The warmth that briefly awakened its frozen surface is gone. The coma that made it visible to our telescopes has dissipated. The tail has vanished. Once again, it's just a dark, silent chunk of ancient ice, invisible and alone, exactly as it's been for billions of years. By 2028, it will cross Neptune's orbit and enter the realm beyond planets, that vast frontier where the sun's influence fades to whispers. And by the 2030s, it will be so far away that even our most powerful telescopes won't be able to detect it. 3I Atlas will return to the darkness between stars, carrying with it secrets we'll never uncover. Stories we'll never know, mysteries that will remain forever unsolved. But here's the extraordinary thing. Even as this visitor departs the revolution it helps spark is just beginning. Because 3I Atlas isn't the end of anything. It's a preview of what's coming. If this journey through cosmic discovery has moved you, inspired you, or changed how you see the universe, leave a like to honor this ancient wanderer's brief visit. And subscribe, because the story of interstellar visitors is far from over, and you'll want to be here for what comes next. Let's start with a number that should make you pause statistical models based on our detection of 3 interstellar objects. In 8 years suggests that at any given moment, there could be 1 to 3 such objects passing through the inner solar system within the orbit of Mars. Think about that. Right now, as you're drifting towards sleep, there might be another ancient wanderer from the stars silently passing through our neighborhood, and we just don't see it. Not because it's too far away or moving too fast, but because we're not looking in the right direction at the right time with the right instruments. This is the fundamental challenge of interstellar object astronomy. We're trying to find needles in a haystack the size of the solar system, and the needles are moving at bullet speeds through 3-dimensional space. Oumuamua was discovered when it was already leaving. We got lucky with its geometry and our telescope pointing. Borisov was spotted by an amateur astronomer with equipment. He built himself, checking the same patch of sky repeatedly. 3I Atlas was found by Atlas, a system specifically designed for this kind of detection. But even then, it nearly slipped past unnoticed in the dense star fields near the galactic center. We need better surveys. We need telescopes that can scan larger areas of sky more frequently with greater sensitivity. And they're coming. The Vera Rubin Observatory, currently under construction in Chile, will revolutionize how we search for transient and moving objects. When it becomes operational, it will photograph the entire visible sky every few nights using an 8.4-meter mirror and a camera with 3.2 billion pixels, the largest digital camera ever built for astronomy. It will detect objects far fainter than current surveys can find, and it will do so automatically using sophisticated software to identify anything that moves or changes between images. Vera Rubin is expected to discover thousands of near Earth asteroids and comets every year, but hidden in that data stream will be the truly exotic objects, the interstellar visitors. Based on statistical models and Rubin sensitivity, astronomers estimate it might detect 1 to 5 interstellar objects per year once it reaches full operation. Imagine that within a decade we could go from having observed 3 interstellar objects in all of human history to having dozens in our catalogs. But quantity alone isn't the goal. What we really need is early detection, finding these objects when they're still far from the sun, giving us months or years to study them, and potentially launch missions to intercept them. This is where the Nancy Grace Roman Space Telescope comes in. Launching in the mid-2020s, Roman will conduct infrared surveys from space free from atmospheric interference, able to detect objects that ground telescopes miss. Its wide-field camera can image areas of sky 100 times larger than Hubble in a single shot, making it ideal for finding rare fast-moving objects. Combine Vera Rubin on the ground with Roman in space, add in next-generation systems like the future extremely large telescopes with mirrors 30 to 40 meters across, and we're entering a golden age of interstellar object discovery. We'll move from finding a few objects per decade to finding multiple objects per year. We'll detect them earlier, track them longer, characterize them better. And crucially, we'll start to see patterns that 3 data points can't reveal. Because here's what we really want to know. Are interstellar objects like 3I Atlas common or rare? What's the typical composition of material ejected from other star systems? Do different types of stars produce different types of interstellar wanderers? Can we trace these objects back to their origins and identify which stellar systems they came from? Are there objects out there that don't fit any category? We recognize things that challenge our understanding of planetary system formation. Right now, we're in the stage of interstellar object science where we're still shocked by each discovery, where every object is a revelation. We're like early naturalists exploring a new continent, cataloging species one by one, marveling at each discovery, without yet understanding the ecosystem that connects them. But as our sample size grows from 3 to 30 to 300 patterns will emerge, we'll develop a taxonomy of interstellar objects. We'll understand what's typical and what's anomalous. We'll learn things about planetary system formation throughout the galaxy that we could never learn by studying our solar system alone. And here's something that excites me deeply. Every interstellar object carries information about stellar evolution. Think about 3I Atlas, with its estimated age of 7 to 14 billion years. If it's really that old, it formed when the Milky Way was young and chaotic, when the first generations of stars were dying and enriching the galaxy with heavy elements. The composition of its ice, the ratio of different isotopes, the organic molecules it contains, all of this is a fossil record from that ancient era. Now imagine we detect hundreds of interstellar objects and measure their compositions. We could sort them by age, by chemical makeup, by origin region in the galaxy. We could construct a timeline of galactic chemical evolution, watching how the mix of elements changed as successive generations of stars lived and died. We could test theories of stellar nucleosynthesis, the processes by which stars forge heavy elements. We could map the structure and history of the Milky Way in ways currently impossible, all from studying cosmic ice balls that happen to pass through our neighborhood. There's also the planetary defense angle that grows more important with each passing year. We're getting better at detecting potentially hazardous asteroids, objects from our own solar system that might strike Earth. The DART mission successfully demonstrated that we can deflect an asteroid by slamming a spacecraft into it. Future missions will test other deflection techniques, but all of these capabilities assume we have years of warning time to launch a mission and apply gentle forces that gradually change the asteroid's orbit. An interstellar object on a collision course with Earth presents a completely different challenge. We'd have weeks, maybe months of warning, not years. the deflection energy required would be orders of magnitude higher because of the extreme velocity. Traditional techniques might not work. We'd need new approaches, new technologies, maybe even controversial options like nuclear explosives. The probability of such an impact is vanishingly small, far lower than the asteroid risks we actively track. But it's not zero. And working through the scenarios, developing response plans, testing our capabilities against interstellar visitors like 3I Atlas helps us prepare for the unexpected. But let me shift gears and talk about something more philosophical, because the implications of interstellar objects extend beyond science and defense. They change how we think about place and belonging in the cosmos. For all of human history, everything we studied in the solar system, every planet, moon, asteroid, and comet shared a common origin. They all formed from the same primordial cloud of gas and dust that collapsed 4.6 billion years ago to form the Sun and its family of worlds. We're all cousins, products of the same creative event, bound together by gravity and history. But interstellar objects are outsiders. They come from elsewhere, from star systems light years away, carrying material that formed under different conditions around different suns. When we study 3I Atlas, we're not studying our own solar system's history. We're studying someone else's history, touching material that has nothing to do with Earth or the Sun or anything familiar. It's the closest we've come to physically sampling another star system without actually traveling there. And that's profound. It means the galaxy is more connected than we imagined. Matter doesn't just stay put around its parent star. It gets ejected, it wanders, it visits other systems. The stuff of other worlds passes through our neighborhood. And if their material visits us, our material surely visits them. Right now, there are probably chunks of rock and ice that formed in our solar system, drifting through interstellar space, passing by other stars, maybe even being observed by other astronomers. This creates a kind of cosmic commons, a shared inventory of material that belongs to no single star system, but to the galaxy as a whole. And if we're serious about exploring beyond our solar system, if we dream of sending probes to other stars, we don't necessarily need to travel light years to sample alien worlds. We can study them when they come to us, when gravity and chance bring them within reach. That's the vision behind missions like Comet Interceptor. That's why proposals for fast response interstellar intercept spacecraft keep appearing in mission concept studies. We're developing the capability to do close-up science on objects from other stellar systems without leaving our own. It's not the same as going there, but it's a start. It's a way to bootstrap our knowledge, to learn about the galaxy's diversity before we have the technology to visit distant stars directly. Now, as 3I Atlas fades from our instruments and continues its eternal journey, I want you to think about what it represents. This object is a messenger, not in the sense of carrying information deliberately encoded by aliens, but in the sense that its mere existence tells us something important. We're not isolated. Our solar system isn't a sealed bubble cut off from the rest of the galaxy. We're part of a larger ecosystem, connected by the slow exchange of matter, by the wandering of orphaned worlds, by the deep gravitational currents that shape galactic structure. For billions of years, objects like 3I Atlas have been passing through our solar system unobserved. They've drifted by in the darkness while dinosaurs walked the Earth, while continents shifted, while the first stirrings of life emerged from ancient oceans. They've witnessed our planet's entire history from a distance, silent observers, to the drama of evolution, climate change, mass extinctions, and the eventual emergence of a species capable of building telescopes and pointing them skyward. And now, finally, we see them. We track them. We study them. We send spacecraft to observe them from multiple vantage points. We coordinate international networks to extract every possible bit of information from their brief passage. We argue about what they are and what they mean. We dream about intercepting them, about riding along with them on their journeys through the stars. This is what it means to be human in the 21st century, to have one foot planted firmly on Earth, dealing with all the challenges and conflicts and mundane concerns of daily life, and the other foot reaching toward the cosmos, grasping at mysteries billions of years old, daring to study things we can barely comprehend. We live in the overlap between the ordinary and the extraordinary, between the terrestrial and the cosmic, between the known and the unknowable. 3i, Atlas won't remember us. It's not sentient. It doesn't think or feel or care that for a few months a young civilization on the third planet from an average star noticed it passing and turned their attention toward it with wonder. But we'll remember it. It's now part of our story, part of humanity's collective memory of learning to read the messages written in starlight and ice. What comes next is up to us. Will we continue building the telescopes and spacecraft needed to study these visitors? Will we fund the science support, the researchers maintain the international cooperation? Will we ask the questions that matter? Not just what these objects are made of, but what they tell us about our place in the universe, about the nature of planetary systems, about the history of the galaxy, about the potential for life beyond Earth? I believe we will. Because curiosity is as fundamental to human nature as breathing. We can't help but wonder what's out there, what secrets the universe holds, what stories are written in the ice of ancient comets. Every generation asks these questions in their own way, with their own tools pushing a little farther into the unknown than the generation before. And sometimes, if we're lucky, if we're paying attention, if we have our instruments pointed in the right direction at the right time, the universe answers. A faint dot of light appears in our images, moving against the background stars. Calculations reveal it's not from here, not bound to our sun, traveling at impossible speeds on a trajectory that originated light years away. And for a brief, precious moment, we get a glimpse of what's out there in the dark between stars, wandering ancient, unknowable, beautiful. Thank you for joining me on this journey through the story of 3i Atlas, from its near-miss discovery to its eventual departure into the cosmic darkness. Thank you for caring about these mysteries, for being the kind of person who finds wonder in frozen balls of ancient ice, racing through space at 152,000 miles per hour. Thank you for being curious about the universe and our place in it. As you drift off to sleep tonight, I hope your dreams carry you beyond the familiar, out into the space between stars, where wanderers like 3i Atlas spend eternity in darkness and cold, waiting for their next brief encounter with a sun, their next moment of warmth and light before returning to the void. And I hope you wake tomorrow with a renewed sense of wonder at the cosmic ocean we're only beginning to explore. The universe has more stories to tell, more visitors to send our way, more mysteries to reveal. And I'll be here ready to share them with you, to explore them together, to continue this journey of discovery that defines us as a species. Sleep well, stargazers. The cosmos is vast, ancient, and full of wonders we've only begun to imagine. And somewhere out there beyond Neptune's orbit and heading toward infinity, an ancient comet carries on its journey, indifferent to our fascination, but forever part of our story. Until next time, keep looking up.